Welcome to another coding session. This will be a short one because it's already in the evening. I thought I would refactor how compile time execution works in Plum, my programming language. So what is compile time execution? In many languages, like in C or Rust or Zig or anything, the compiler may choose to execute some of the code at compile time. For example, here we add 2 plus 3 to some number, and in the generated assembly we just add 5. So the compiler just executed this code at compile time. And this also works for some code of not arbitrary complexity, I think, but for more complex code as well. So if we say, or if we curse the Fibonacci thing, I don't know, like if n is 0, then we return here's 1. Something like this, I don't know. Otherwise we're going to return n minus 1 plus Fibonacci of n minus 2. This is some Fibonacci calculation. Okay, and this will actually not be optimized. But if we say, hey, please optimize as much as possible, then there is a lot of stuff here suddenly. Hey, what if we call Fibonacci with 2? We actually call that. Here's the square function, and this just, it adds 2 to the argument, because Fibonacci of 2 is 2. Yeah, but what if we actually do something Fibonacci of 8, maybe? No, that looks like, like it calls Fibonacci. Okay, so there's some limit where the compiler says, hey, I'm just gonna add that. No, still calls Fibonacci. Interesting. This is really interesting. Huh. Well, okay. So at least, for some short code snippets, like, this won't take long to execute. The compiler actually optimizes that call. So it executes this function at compile time. And some languages, like Zig, for example, they even guarantee that certain code is executed at compile time. So in Zig, for example, you can, let's not do any vector stuff. Let's say we have some function that takes some int and returns an int. And it's actually going to return that int plus Fibonacci. What is going on here? Yes, there is no s. Oh yeah, fib doesn't exist. That is indeed true. So Fibonacci of some n. Really? Gotta re-implement that. Well, at least now I have some experience in that. Okay, the point being that here, this foo thingy actually calls, the Fibonacci function. But we can write Comptime here, and then it's guaranteed that the compiler will, it will execute that Fibonacci call during compile time. That's not actually what I expected. Hang on, like 55 or something like that is what 55, okay. Yeah, so in Zig there's a way to force something to happen at compile time. And this is not just an optimization or a hint to the compiler, but the language semantics depend on that. because you can also, for example, have compile time known variables like this, and then you have something. Yeah. And in here, because this is compile time known, this code down here will never be reached. Whereas, if this is not 55, then the Zig language actually guarantees that this code will not just not be omitted in the binary, but not even be type checked. So in here we could do something like compare, I don't know, or get some string and then say .foo, which this doesn't exist. Like, you can write this in the code, but it doesn't make any sense. But the code still compiles, because this Comptime keyword guarantees that this is executed at compile time. So this is guaranteed to be a compile time value. So this if condition is guaranteed to be compile time known. So at compile time, that is the compiler will choose whether to execute that if code or not, and that will actually affect the semantics of the language. In C, something like this would work. In Rust or C++ or something, because there, even if code is never used, this parse all the code and analyze and type check that code is separate from the compile time execution, which is more like an optimization. In Zig not. In Zig these are interwoven, and the language semantics depend on the compile timeliness of values. And my plan initially was to do something similar in my language, because the cool thing that this allows you to do is to actually have a function that accepts some type, and it does something with that. Or like accepts, let's say, 964. And basically it checks, let's check if t equals 55. Then we're gonna return the type to 8. Otherwise, we're gonna return the type to 16. And you could actually create a variable. This doesn't work because this is missing a type annotation. And it's not used. Okay, well, but you can actually use something like this as a type annotation. Yeah, it's not used. That's true. Okay, we really have to underscore that, maybe. No, okay. Yeah. So this works. So you can have first class types, just types as normal values, as long as they are executed or passed around and worked with at compile time. At runtime, you can't have any variables that store types, for example. But at compile time, sure, why not? Yeah, and that makes for some very flexible design decisions. So I wanted to do something similar in Plum. And my initial idea was that, the compiler would just specialize functions if some of the parameters were compile time known. So in this case, for example, the compiler would see, oh, C is compile time known, so I should execute bloop at compile time. And it turns out that does not work well in all cases. Just to give you one example, and hang on, let me get a window with syntax highlighting for Plum. I still have a cold, by the way, so yeah. so this is some Plum code. And I'm just gonna make some space in here. You could write, some function. Let's say an add function that takes an a, which is an int, and a b, which is an int, and it returns an int. But rather than being implemented in a sane way, let's actually say that it makes use of two other functions. Increment of some number. I'm not going to implement that here, and decrement. And this one that basically increments the number by 1, and this decrements the number by 1. So increment of 3 is 4, and decrement of 4 is 3. So you could do something like this. You could say, let's compare a with 0. Plum uses prefix syntax for everything. And then we switch on that, and there were basically two cases. Either a is 0 or it's not. And if a is 0, then we're just going to return b. Otherwise, we're going to recursively call add with decrement of a and increment of b. And for the sake of it, let's just assume that a and b are supposed to be positive numbers. And basically my idea was that it would be cool if if you write something like add 2, 3 in your code, that this is guaranteed to be executed at compile time, to be 5. And at the same time, if you have some, parse function that accepts some JSON, and similar to Zig, a first class type, then you could write something like this. Basically, you could have, if you call this parse function with a compile time known target type, and this is something I even wrote in the README, I think. Yeah, parse that accepts some JSON at a target type. Then you could, at compile time, ask, hey, give me some information about this type. And this is a function that only works with compile time known things. So if you call parse with some type that is not known at compile time, this would actually be a compiler error. So you would get, the compiler would yell at you, hey, from this position, parse was called, and that calls type info with a runtime known type, and that's not allowed. So this can only be called at compile time, but then you can basically, compile time switch on that. So for example, if you call parse of some JSON and a compile time known int, let me just copy this code, I guess. If you call parse JSON with your runtime known JSON, but target is known to be an int, then this returns an int, and we say, hey, type info of int. Type info is called at compile time, and that's going to return an enum with information about what kind of type is this. And this would just return the enum value int. So then we switch on that, and that's compile time known, so we only compile this branch. So essentially we would just get a function that this is compile time known, but this one is runtime known, and it would switch over this runtime known JSON value, assuming that JSON is some sort of enum, and for anything other than a JSON number, it would panic, or it could also return a result or something, otherwise it's going to parse that number and return that int directly. That's the idea, that as soon as you have this guarantee that if some parameters of a function are known at compile time, like this int, then functions are specialized for that. Turns out that fails for this add function. If in the case where both of these are compile time known, that works. Well, let's assume you call, add with only a runtime known a, but the b is compile time known to be 2. well, this function would get specialized for that. So what would actually happen? We would say, okay, we compare a, which is runtime known, with 0. So we would actually compile the comparison function for some runtime known a and compile time known 0. We would compile this, specialize the equals function basically. Yeah, we don't know the value of that though, because a is runtime known. So we would need to compile both branches of the switch. And that means that we call, in this case, we just return 2. And in this case, we call add of decrement of a. So we specialize decrement for int, returns an int, and increment of 2. And hang on, we can we call that and optimize that, specialize that to 3. But then we would basically be okay. So now we need to, specialize this function, add for a and 3. And then we would do the same thing and try to specialize a for some int, runtime known int, and 4. And then add for some int and 5, add for some int and 6, 7, and 8, and 9, and we would never stop. So, I was aware that specializing functions, if some of the arguments are known at compile time, that would of course, increase the amount of code that you generate, because you have these specializations of functions. But in some cases like this, that can actually lead to an infinite blow-up of code. And that might cause the compiler to never stop compiling. It will just compile forever. Obviously, that's not something that we want to do. So my solution to that is, and I've thought about this a bit, is to only specialize functions if all parameters are known at compile time. And I think that's actually a sane approach. Oh, yeah, let's first look at how Zig does that actually. So in Zig, if you have some function like this, if there is no Comptime keyword here, I'm not actually sure if this will compile. This will not compile, because this is not compile time known. So here you have to specify at the call side that you want this to be compile time executed. And the way that works is, depending, Zig behaves differently depending on the context. Like here it sees, okay, I have this variable of the type this here. And then it knows, okay, this here must be compile time known. So I'm actually going to call bloop at compile time. And there were some other cases, like if a function expects some sort of type, for example, then the function is specialized for that type, because types can only exist at compile time, or you're in a compile time context like here. So there were these handful of situations where the compiler will execute at compile time. Otherwise, that's not the default behavior, like you can see in here. I think that's not even, if you put a 1 in here, like this doesn't depend on the semantics, they don't depend on the complexity of the computation here. There was really like a language spec of, hey, if you call some function, the compiler will just treat that as a runtime known value. Even if later on in the optimization pipeline, we will actually execute that at compile time. Okay, so yeah, you can kind of fix that by saying, hey, this function here expects a Comptime known parameter. And then when you call this function, oh, this is interesting. The n is known at compile time, but the function value, that basically means that, this function, oh, come on. This function, in here, you can do things, you can, for example, do, I don't know, t, some type, is, can you use if as an expression? I'm not actually sure. If n is 0, then u8, else u16, and then use that as a type annotation. B is not used, I know. But this function type checks, because the compiler, just by analyzing this function in isolation, knows that n will be compile time known. So it will actually be like, okay, so this is either U8 or U16, so any type, and then this type checks and so on. Yeah, whereas if we don't have this, then this will say probably, because this is during parsing, I think. Yeah, if I mangle that somehow, it will basically say that, hey, T is not compile time known. It may not be compile time known. So comptimeness of parameters is a part of the function signature in Zig. I don't want to do that in here, because comptime is really just for rare cases. You know, in Zig, comptime is even used for generics, like, you know, you have some, I don't know, array list function that takes a T, which is a type, and returns another type, and so on. And then you can use, you know, array list U8 somewhere. Like, I have generics in Plum, and because I want function overloading and, you know, some other stuff. So I don't use this comptime stuff as extensively as Zig, but only for cases like, you know, formatting arbitrary types or writing JSON parsers or stuff like that. And I think for those cases, it's sufficient to split your function into two parts. Basically have, you know, instead of one function where we expect that it will be specialized for some of the parameters being compile time known, we'll actually have only the guarantee that if all arguments to a function are compile time known, then that function will be executed at compile time. So you would have to split this function into, you know, basically a function JSON parser that accepts a target type, and then it returns you a JSON parser, like, you know, a lambda, which are written like this, that accepts JSON and returns that target type. Yeah, and you would basically just do this, like a lambda. I don't even know. That accepts JSON and returns, and then you basically have this body in here. So you can always, you know, manually sort your parameters and basically have two nested functions. The outer function that runs at compile time, and then it returns a closure that accepts the runtime known arguments. Yeah. And I think in many cases that's actually like pretty sane or pretty reasonable, you know, like you create some sort of parser at compile time, and then the parser function runs at runtime. Like that is intuitive, I think. Yeah. But basically my point is that first of all, developing your own language is cool because you really, really understand the design decisions of other languages. Like before, when I was just looking at Zig, you know, I was kind of blown away by the Comptime stuff, but I was wondering, like, why does it require Comptime annotations in several places and not in others where I expected it to? And you know, trying to design your own language basically makes you really think about the trade-offs and the edge cases of these different, you know, language features. So yeah, I recommend, you know, create your own programming language. It's not just a lot of fun, but also you'll get such a deep understanding of the trade-offs of existing language features. Something else I wanted to say. Yeah. Also, the second thing I wanted to get across with this is that because I have no idea what I'm doing here, like I'm just figuring this Comptime stuff out. The features are like Comptime in Plum changed quite dramatically, as well as, by the way, the type system of Plum and some other stuff. Like, this is a language that was not designed, in isolation, in a vacuum, and then I try to implement that. But this is really an exploration of, hey, I want to play around with this Comptime thing and specialization. And I think this, this kind of thing of just nesting functions is a fair trade-off. The concept, by the way, is also called currying. It's very common in Haskell. It's named after some dude, Haskell Curry. Maybe? No way. Oh yeah, Haskell Curry. Dude. That's crazy. Okay. Yeah. First name and last name are famous in programming. Crazy. Okay. Yeah, but basically, if you have a function that takes an x and a y and produces a z, then you can basically split that into into a function that takes the first argument, x in that case, as a parameter, and then creates another function that maps y to z. Yeah. So basically, if you have something, like we have a function that parse expects some compile time known type and a JSON value which is okay to be runtime known, then we can split that into a function that accepts a compile time known type, and that will be guaranteed to run at compile time, and that returns another function that then expects a runtime known JSON value and turns that into something. Yeah. Alright, so because this entire Comptime story for Plum grew quite organically, the code is not optimal, I would say. So let's just look at that. And that's the, something to your good, yeah. In here, we can see that, by the way, the compiler stages should give a quick introduction. We have this expression guided graph, which contains like untyped values, basically. Like, it's a graph of the code, like, names are resolved and so on, but things don't have types yet. And then we can type check that and convert that into the yogurt, where everything has like strong types and there are explicit casts in there and so on. And oh yeah, we also do function overloading in here. But basically, in here, when we compile a function, we actually have, hang on, where's the compilation function? Egg to yogurt of egg. Yeah, we have some function from the egg and we want to convert that to a yogurt function. Then we have these parameters in here, yogurt params. And would oh, hang on, the yogurt params are not in here, but they are in the yogurt probably. Yeah, they are these things. Either runtime known or compile time known. And that made sense, like that exactly models the original idea of, hey, we want to specialize a function where some of the parameters are known at compile time and some are only known at runtime. But it doesn't really model how I think about compile time execution now, where either all parameters are known at runtime or all of them are known at compile time. And it makes things, like this design makes it a bit difficult in other cases. So for example, if we have a call, then we will actually see, hey, are all of the arguments compile time known? And then at some point, I'm not sure where, yeah, there's an exception, the built-in type of function. There we basically want to treat the function, like execute that at compile time, even though the argument to that function is only known at runtime. Because you should always be able to get the type of some value, and that returns you a type, even if a type that is compile time known, even if the value is only runtime known. But yeah, this is the type of function. I kind of have to think about that a bit more. Maybe I'll make that a more ingrained language feature rather than just a built-in function. I don't know. But anyways, if this is supposed to be a Comptime result, hang on, do we compile the function here? Oh yeah, we do. Oh, okay, yeah. So we checked if all parameters, like all arguments, are compile time known, and then these are the yoked params. And this, I did something hacky. I'm not entirely sure where. So we go through all the parameters, and if that's compile time known, then it's just if false. Well, if it's compile time known, okay, it's just always going to be runtime known. Yeah, basically when I realized that, oh shit, this doesn't work out the way I expected it to, with the add function and this blow up, I just very hackily disabled that Comptime specialization here. Yeah, so these are all runtime known, and yeah, the function is specialized in something, and the compile time result. Like in the normal case, we would actually emit a call to that function. But if the result is supposed to be compile time known, then what we would do is we would also push a call. But then we would go into that compiled function and see what is the returned expression there. And we would just assume that that is a compile time, like a Comptime expression. If not, that's an error, like a bug in the compiler, basically. Because if we specialize a function for all compile time parameters, then the result expression should also be a Comptime expression. And yeah, we would also push that compile time expression in here. And this is super hacky. Like, we just compile this function in this very generic way. Currently it's just always runtime parameters, but it accepts a mixture. It is more, the function is more general than it needs to be, this toYogurt function, because it doesn't actually need to be able to compile functions where some of the parameters are compile time known and some are runtime known. And also, if all of them are runtime known, we actually want to get the value of that and just not emit a call in here, but just emit that value directly. The reason that we still do the call in here is that functions can have side effects, and that's not really. Like, Plum is a language where functions basically don't have side effects except this one nasty effect, which is that they can panic. So we can't actually just not call the function here, because if there's if the function is like assert that something is true, or something is true, and then it returns 3, then otherwise we would just insert the 3 in here because it's compile time known that this function returns a 3, but actually the function is going to panic before that. Yeah, that's like, this is super hacky. Like, in general, just inspecting the body of this function, of this compiled function. This is ugly. So what I want to do instead is basically, where was that initial? Yeah, basically split this function in two. Have one, basically that converts, I don't even know, like yogurt, 1 to yogurt runtime, I don't know, and 2 yogurt Comptime, or like run at Comptime, something like this. And this is more like compile this function. Yeah, and we don't need any parameters because these will all just be type parameters. Yeah, and yeah, we do need, like, using these substitutions, we can actually specialize the function. If this is a generic function, then we still want to specialize that to concrete types, but not to concrete values. Okay, so yeah, that's basically what I want to do. Split this function in two. Basically, have one compile function and run at Comptime function that expects a function and just arguments, which will just be Comptime yogurt values. Maybe substitution, I guess, yeah. And this will not return a yogurt fun. No, it will return a yogurt Comptime result or something. And this is either going to be the function panicked with a string, or it returns this value. And then in the surrounding function, where we call a function with all Comptime known arguments, there we basically insert, either we insert the panic message in there, or we just insert the return value. Yeah. We basically handle these two cases and do the appropriate thing. Okay. Yeah, should also, like, halts is also an option. Like, the function can, if the function at some point recursively calls itself, we should detect that and not just hang the compiler forever. I'm not sure if that's, let's make that an error for now. And yeah, if that should be allowed, we can also add that later on. Okay. True. So let's maybe adjust the yogurt, I guess. Yeah, we don't have any yogurt params anymore. That's not a concept that we need. Yogurt signature refers to yogurt param. But that type doesn't exist. True. Like params, yeah, this will just be yogurt types. Can we even do that in a single line? Yeah, we can. Amazing. Yeah, and these will always be basically runtime types. So yeah, something like this. Cool. Oh yeah, yogurt type is not a thing. Instead we use plum types everywhere because the types are consistent among all compiler stages. So let's to expression refers to yogurt param, but that doesn't exist. True. Let's just remove that and see what else breaks. To yogurt of an egg body using some parameters. Ooh. The body is also, egg bodies are also used for switch statements. But I think that's actually fine, right? Yeah, I think we don't need that here. Nope. We could just add yogurt IDs here and make, adding these IDs a responsibility of the caller. I think I like that. Yeah, let's do that. Let's just say these, the parameters to that are some yogurt IDs. Then we move that to the compile function. Yeah. So basically here, params. Params doesn't exist. We can take the egg fun and specialize that. So params is a list of types, and for param and egg fun, params do param.specialize using the substitutions, and we push that to the params list like this. I hope there's a specialize. But apparently there is. Yeah, and then let's convert that to a slice. Okay. Then in here we have yogurt funds dot put. Put signature yogurt fun. Wait, this is just a placeholder. Yeah. Okay. To yogurt refers to yogurt param, but that doesn't exist. true. Yeah, that is very true. I mean, this could just be yogurt types, I guess. Makes sense. I'm wondering though, what do we do with these? Oh, to expression. Yeah, that doesn't. It can be Comptime things, and then we use that here. Do we want to specialize built-ins? Maybe not directly, actually. You know, maybe we don't. Yeah, no, and here not. You know, we can add an optimization path later on that folds some constants and so on, but not. I think that's not something that we should just do by default. Yeah, so let's say your archetypes, those are actually just types, which makes sense. Why was that something else? Like, and also let's just call this params to make it consistent with this one and this one up here. Okay, yeah. Okay, so we have yogurt IDs, and this will just be yogurt param, no, yogurt op param dollar. Very cool. Okay. So yeah, these are always runtime known parameters. And yeah, well, this means we do less optimizations than we do currently, but that's fine, I think, because now we have this extreme, narrow, formal distinction between a compile time context and a runtime context, and this is for a runtime context. Okay. Yeah. Instead of all this code that checks, oh, is this Comptime, then we do other stuff. This gets a lot simpler. That's cool. I like that. Oh. Noise. Yeah. Oh, hang on. This all references A and B. What did I do? Oh man. Yeah, we do need A and B. We just don't need these Comptime checks. Okay. crazy. Oh yeah, and for the type of thing, it's just always gonna be, you know, the type. Cool, very cool. Type info. Oh, this is supposed to only run. Oh, this can just run. Can just return an error, like basically this. Because this entire function here is only for compile time known values. Very cool, actually. Nice. All right. So code gets simpler. That's super nice. First yogurt type. No, that's plum type. Yeah, yogurt param doesn't exist because now the arguments. Yeah, the function overloading is only based on types, not on values. I think that is same. Yeah, it does mean that you can't have this. You can't do something like this. A function foo that accepts some t, which is a type, and then foo, which is that t, and does something. But I think it's very fair if we say this is not possible. Something that is used both as a value and as a type in the same signature. In here, like all of these things have to be independent, like concretely typed, or like even it can use generics, like type variables, which are lowercase. But these values and types are not of the same domain, basically. We can allow that, this, like some of these are used in the return value. I think the return value is kind of special because this is not used for overloading. I mean, theoretically, we could even say that, in some cases the return value is allowed to be computed, or it's going to be some function call in here that then runs at compile time. But like in general, I think for the actual arguments of a function, which are used for compile time and like for overloading, we shouldn't allow any shenanigans there. Okay, so this will just be types. Yeah. Okay, so so in this, first look for functions where the name matches, and then we gather constraints. Yeah, if the archetype is the type, then we add the constraint that the name has to be the type. We don't have that now. I mean, hang on, we could still do that actually. We could still allow this. Do we want to, though? I mean, the code for that is already in there, Oh no, but this is only if this is a Comptime thing. So yeah, no. Oh, we can just remove this. Yeah, but .a, the args, is some Comptime thing, which it never is. Yeah, let's just remove that, and then we have this. Amazing. So if this is, we don't need to switch on that. This is always a runtime known type. Oh. Yeah, these args are just the types. So we can just call them args. This is pretty amazing. Pretty amazing. Okay. Yeah. So, where are errors? Like I was expecting more errors to be shown. So we want to run the Martinez compiler to then run our Plum compiler. Param doesn't exist in Yogurt. That is indeed true. Yeah, this doesn't make any sense. Just remove that. Sure. This definitely fits on a single line, yeah. So here we do some stuff. What's going on here? Yogurt param is not known. Okay, let's just do a full search of yogurt param. Where's that used? Oh, in lots of places. Okay, so converting yogurt to an, this entire this function called to yogurt. I'm actually gonna turn these into something more special, like compile. That is more focused on the action that we're doing, the process, and we compile that, not just we convert that to something. That this is a stronger verb, so I think that makes the code easier to read. Yeah, okay, anyway, so what we do here is we look for a main function that, it just expects types. So, boom, a main function that accepts an int, and that's it. Easy. And similarly here, we convert that main function to yogurt. How do we compile that? And yeah, let me rename all to yogurt functions, maybe. So we have this egg body. Let's compile that. Compile. Boom. Strong verb. Expression. Yeah, let's compile that. Built-in. Let's compile that. And built-in again. Let's compile that. So we have a bunch of compile functions. Then we also have the run at Comptime function. So I think I'm just going to call this run. So we have basically here functions for compiling code, compiling code. And here we have functions for running code at compile time. And this will be like two separate modes, that call into each other. And above that we only have lookup looking things up in the egg, like these are just helpers basically. Yeah, converting the creating yogurt values, having this builder thingy. Yeah. Okay, so that compile thing will actually be down here. I'm not sure about this compiler. Possibly a fun builder and a compiler. Yeah, let's do that. Yeah, let's do that down there as well for compiling code. Okay. Yeah, so we have a run function and a compile function. That's pretty cool. Nice. And then in here, let's see, lower all cases. Oof, so this is a switch. We look at the condition, look at the variance. We lower all cases. Of that switch, okay. Switch.cases.get. Okay, the question was basically if we have, like a compile time known value, and we switch on that, like an enum value that is known at compile time, then yeah, I do think we want runtime values for these arguments. Weirdly explained, but yeah. Oh, hang on. So here we... Oh, this is horrible. So first we create parameters, and then for the variant type, the payloads, we basically push runtime parameters. And then we check, hey, is the condition, is that Comptime known, and is its value this variant? If so, then we clear those parameters that we just calculated, and we instead fill them with Comptime things. Like this is no. And also the yogurt ID generation for converting something to a body was adjusted. So yeah, this really should be a list of yogurt IDs rather than anything else. Yeah, let's maybe do this check. First. If condition expression.op is Comptime. Well, hang on. Really need to get this. What's going on here? Okay, I think we need to do some conditional compilation, like get this condition out there basically. Yeah, let's say these are just, initially, this needs to be a slice of yogurt IDs. Period. Okay. And then if we move this code up here, so if the condition expression is compile-time known, a compile-time known value, then we get that value's variant. And if that symbol is our key, then we just set. Yeah, we just create params as this down here as a list. I don't know. And we push. Oh, hang on, value to payloads. Oh no, yeah, we just say params equals that. Yeah, no, okay. Actual variant. We know what the condition is that we switch, like the enum that we switch over. Yeah, if that's a Comptime enum value, yeah, exactly. Then down here we say params is params or, and that basically means that if we set that using this, if this was a compile time expression and we set that to some, then we just take that otherwise, and this is where we'll create the list and push these param ops and so on. Just a push yogurt op dot param with that type. And then list to slice. Yeah. And then here we don't need to call to slice because that's already a slice. And then we compile the body. Amazing. Okay, so yeah, this should just be an empty slice of yogurt and some types. Lambdas, yeah. Okay. Params. Oh, now we're at the call. I see. Oh, this is gonna be interesting. Are all args Comptime? True. Okay, so then we see, okay, if they are actually all compile time known. Fair. And then we say, yeah, we don't just want to build parameters and then compile that function and specialize that for things. And then later on see if, and basically look again, oh, by the way, is this supposed to be compile time known? And then we're gonna extract the value from that. But instead we just have one big if in here. We're just gonna check, if are all args Comptime, then we're gonna do something, otherwise we're gonna do something else. And this is gonna be very similar to the part that we do in the else part. Because basically what we're doing is yeah, let's maybe copy this because this may be similar. Yeah, but let's first do the else part. So if this is a runtime call, then let's see, we do compiler egg lookup from types. Args are just yogurt IDs. Okay, so we need to get the arg types. Let's call this arg types and actually call that, like, you know, arg types, and that's gonna be a list of plum types. And for every argument, we're gonna get the type, and we're gonna push that. Very, very, very simple. I really want maps in this language. You know, I like mapping values and, well, anyways. So yeah, then we just look up that function using the argument types. Or if there's an error, you know, no function found or something, then we're just gonna return that error. Okay, then we're gonna compile the function using this wonderfully named compile function. And compiling a function doesn't actually need argument parameters. No, it just needs substitutions and a string, an egg, and yogurt. You can fit on, yeah, that fits on 119, amazing. So then, you know, are all args Comptime? Yeah, we checked that before. Oh yeah. Okay, maybe I copied that some down here. Oh, that was really duplicate code, I don't know. Is this a Comptime result? No, definitely not. This is a call, hang on. Except, yeah, except the built-in type of. Still need to think about that, you know. Run, you know, built-in type of also at Comptime. Okay, so yeah, this is not a Comptime result. So let's just copy, remove this and just emit a simple call to that compiled function. This code is actually readable because it doesn't intertangle this compile time execution and runtime execution. Amazing. Yeah, and in the other case, when all arguments are compile time known, then yeah, this is just copied from below, so we need to adjust that. But okay, then we build the argument parameters. Let's call them just args, and we know that these will be values. Yeah, and we know that these are compile time values in here. Yeah, so we can just unwrap that underlying yogurt value and look at that. relatively readable code. If all args are Comptime, then we actually get those values from there. Yeah. And then we do, call ID. No, we don't actually need to call some function. Yeah. And what did we do? Yeah, this is very similar. And we need to do something like looking up the function and so on. So we are just going to look for a function that matches those types. Hang on. Okay, so we do need to aggregate the types as well. I guess that makes sense. Hang on, we can do that outside of the if, I think. Yeah, we definitely can. Oh, look at this. Call, so we get all args. We get the types. Are they all Comptime known? Who knows? If so, then we get the arg values, I guess. Because args here is really argument IDs, Yeah, and we'll look up a function based on the type. And then we don't compile the function in here, no, but we run that function using the values. Okay, so let's look at the signature of that run function. Takes an egg fun, takes arguments, which are concrete yogurt values, and then some substitutions. I think substitutions are not actually needed, but okay. Yeah, so the arg values will be passed as an extra parameter. And we don't need to call anything or inspect the function and inspect the return thingy and assert that that is a Comptime thing and blah. No. We don't need to do that. Yeah, no. Nope. We can just do... Wait, we can just switch on that. Result is that. Oh no, look up result. Returns, maybe? Oh, no. Ran. I don't like that, but sure. Yeah, so either it panics or it returned. If it panicked with a message, we're gonna do something. Comptime fun panicked. If it returned some value, then we're just going to do this. We don't need to emit a call at all. We'll just push the value to expression. I think something like that exists. Wow. Like this very clearly says what the compile time logic is, We look, are all of the arguments compile time known? If so, then you know, everything's fine, and we just actually run this function at compile time. Otherwise, we, oh wait, that lookup, hang on, oh, amazing. That lookup can happen outside of this, because the lookup is always the same. Look up a function, or we return an error. Oh, is this beautiful? Wow. Yeah, and here we just collect the argument values and then run the function using them, and then just push the compile time expression to the body, the result. Otherwise, we compile the function and we push a call in here. That is pretty amazing. Okay, where else are yogurt params used? In casts, okay. Cast from and to. Oh yeah, and the yogurt, yeah, it does take, arguments, but the syntax for this is just like the yogurt signature doesn't really use those anyways. So plum type. Okay, this is the compile cast function. Okay. Oh, I've seen this before. I should factor that out. So param is body.parent dot push of yogurt param.runtime of from and what's going on here? Oh yeah, yogurt param is just the from type. To expression, okay, so this is a yogurt op dot param of the type from. So this is some expression, I think. Oh, and it's only used down here. That's weird. Let's maybe inline these in here. I think that's gonna be clearer. Yeah. Compile cast fun body. Ah yeah, and this returns some yogurt ID. Okay, sure. Yeah. So then we have this. Oh, okay. Where are we? Compile cast from body. Oh, okay, sure. So if we have an enum, then we also something. Oh, we compile that to to some IDs, apparently. Yeah, but this is all going to be runtime stuff. Do we use this anywhere else? No? No. No, we don't. Hang on, we only use that here. Hang on, let me zoom out a bit so I can really make sure. Params equal. No, we only use that here. So these are just the from payloads then. And instead of pushing it to this list, we can just take this and, you know, instead of pushing it and then getting that again, we can just do this. And this, yeah, this payload in from payloads. Okay. Yeah, so we don't need this. And yeah, this doesn't exist because this, you're converting this to an expression will just result in a yogurt param. So yogurt op.param of the type payload. Okay, yeah, sure. Yogurt ID, maybe inline that even, because why not? Okay, no more yogurt params in here. Let's see what happens. To yogurt, no definitions to yogurt. That is indeed true. So in here we say compile. I think that's actually more. Oh. Was to yogurt fine? I mean, here, I think it kind of, I like that it's all consistent, you know? Converting bytes to a string, converting the string to a bacon, converting the bacon. Like, we could name this, and this is, you could name this parse, for example. That makes sense. And this compile makes sense, but this is also compile, I guess. And this is also kind of parse. So, and this is compile, and then also compile, like, yeah, you know, I think within a single compilation stage, having these compile and run functions and parse functions and so on, that makes sense, and that's like more descriptive. But in this, like the outside API of these conversions, maybe having something like to yogurt is a bit more descriptive instead of just reading .compile all the time. Especially if you, if you're sure that this works, for example, or if we do some other error handling or stuff, you could basically, you could do, you know, to toast and then fail if that doesn't work, or, you know, to egg and then to something. If you just have thank you. If you just have compile, compile, that's not super readable. In this overarching overarching organization, having descriptive names actually, like names that are separate for each stage, actually makes sense. So this egg to yogurt, I like the separation in compilation and running. So I will keep that. Yeah, and having these compile functions and run functions. But I am just going to rename the top level compile function for the entire egg. I don't know where that is though. Egg body, egg something, egg fun, compile egg, yeah. I'm gonna name this true yogurt on this egg. And that's just gonna compile the main function. I think that's fairly reasonable. Yeah, compile the main function for ints. Yeah, that makes sense. Okay. Okay, so this doesn't work because... Oh, it doesn't need the types. Just needs the substitutions. Boom. The substitutions... We looked for a function that matches ints. We don't need to repeat that down here. No. Just compile that main function. Nice. Okay, so then down here we get some expression and we compile that. Amazing. Then in here we have some parameters, but it's an invalid assign. Oh, because these are yogurt values, not IDs. Okay, yeah. Good values, yeah, we need IDs for those. That makes sense. Yeah, rather than list, I'm just gonna call it IDs, just because that's a bit more descriptive. Yeah, I'm just gonna do something very similar up here. Just create IDs, and then for each value, an actual variant payloads. We could even say for each, payload, which is a value, but we push yogurt Comptime of that payload and of that corresponding type. Where does type come from? Oh, here for type in. Hang on. I think we can just do this. And in the end we do that. Oh yeah, that's an expression, and then we need to push that to the body, to the builder, I think. So builder dot push, I think. Yeah, and same thing here. I was wondering why it works down here, but not up there. But yeah, that's just the analyzing capabilities of Martinez. Okay. Next arrow down here somewhere, and that seems fairly reasonable, I think. Creating a lambda compiles the body. Yeah, that makes sense. Oh yeah, these don't exist. We need what are they named? Panicked or returned. Hang on. Let me actually check the run function. Yogurt Comptime result. Yeah, this is inconsistent. Like either these functions are deterministic. So either this function panics for those values or it returns something. But we could also say, hey, we ran those functions and it panicked or it returned something. But I think because this is not... Yeah, I think like using the present tense for that makes sense, because this is a generally applicable behavior of the function for those concrete inputs. Okay, so panics or returns. Your function either panics or it returns. Okay. Then down here, we do yogurt signature of the types, of course. Amazing. Amazing. And then in here, we say something. Param.len. Oh, hang on, here they are types. Oh, okay, so param types, I guess. Param types. Let me move that to the left. So param types, and then I in param types.len. Why so complicated? Why do? Let's rather do this, you know. For type and param types, we just push the param of that type. And these are like param IDs, I guess. Yeah, and then we compile the built-in function. Yeah, you know what, I feel like IDs are kind of the default thing. If something is called args or IDs or payloads or so on, then usually these are just IDs. If there's something else like types or something, then you may think about renaming them. Yeah, so in here params are just IDs, that makes sense. Yeah, and this is also just params.toSlice. And it is already a slice, so just params, I guess. Why is this code so short suddenly? Like the code gets so much more readable. Because of this change, you know, of separating Comptime and runtime stuff out. Let's try to compile that. Yeah, it doesn't work because some type is not found. There is no yogurt type, indeed. Where do we say yogurt type? That doesn't make any sense. No, these should be plum types. Why is that only shown on the command line? That kind of sucks. Okay, so this call doesn't work. This is the signature specialized. Egg param substitutions. Oh, param. Yeah, param has a type. I think. Yeah, there's all these param types. Maybe. And param types is param.type. That is reasonable, I would say. Yeah, and this contains the param types. Amazing. Oh yeah, I wanted to do some. I think we have two places where we have this replace placeholder function. Yep, body is not in scope. That is weird, right? Is it egg funder body? I think so. No, or just egg funder params.len maybe. Why so complicated? Oh, I see. why not, you know, iterate over the egg fun params directly, but we need the I for something. I'm actually not sure, to be honest. And we have the param types. Yeah, this is not supposed to be params, but something else. The question is what? Oh, before it accepted params. I see. Oh, so we say param types get I. That's a type. Oh yeah, and that's a yogurt op param of that type. Yeah, that makes sense. Or not. That's a yogurt expression. True. Yogurt fun builder. This has to be mutable, maybe? Yogurt fun builder, yogurt expression. Yeah, why is that not? Oh, it is really not. Interesting. Did we copy this code maybe from... Oh yeah, this entire code is new. Okay, so... Yeah, it makes sense. There were some errors in here. Yeah, and same here. Sure. Sure. This call doesn't work. Yogurt code compiler, egg param, yogurt ID. Egg ID is what? What? No. Egg param contains name and type. Hang on. Before these were egg, we need egg IDs apparently. What is the egg ID of that? I think it's eggfun.body.params.getI. Body is not a field. Yeah, hang on. Oh, code, maybe. Code.body. Oh, amazing. Yeah. And let's maybe actually zip these params with the param types. I think that makes sense. Yeah, okay. So group in here, let's actually zip the egg from params with param types. And then the first one is just the egg ID. Hang on, let me check if that's actually correct. No, code body params is what we actually want. and the type of that is in here. Amazing. Okay, and then we compile that body. Okay, egg body doesn't work because this is a list, and let me guess, it expects a slice. Yeah, okay, we can deal with that. Oh, there were still errors down here. Built-in to yogurt of params. So if this thing is a built-in, then what does the built-in expect? Param types, right? Yeah, I think the built-in, when we compile that, by the way, what we do is compile that for specific parameter types. Okay, it compiles, but it doesn't run. Okay, so to do, oh man, that is what, compiling main int, and then it tries to run some, oh yeah, it compiles the main int. Okay, so it compiles the egg to yogurt, so it compiles the main function, compiles its body, compiles some expression, and that means it wants to run some other function at compile time. Yeah, so this entire compile time stuff still needs to be implemented. Yeah, maybe let's print the function. Or I don't know, name, and so args dot debug, I guess. Do your values have, they probably implement right? Yeah, they do. Okay. So we can actually see the kind of, oh yeah, we want to call this function at compile time. List with the arguments 1, 2, and 3. That is amazing. And then, because we execute this, we don't actually need we don't need to compile that list function to some code that is then optimized for, that just has a bunch of Comptime expressions inside. No, we just keep track of that on the fly and then throw that away and just keep the result around. Damn. Okay. Yeah, so how do we do that? I guess we need basically a very trimmed down version of the yogurt code compiler and so on. Like, we don't need mappings from egg ID to yogurt ID, for example. But we do need a mapping from egg to yogurt value, basically. So for each egg expression, we will just figure out the value. I guess values, and that's just a map from egg ID to yogurt ID. Simple. And yeah, okay, add mapping, lookup, stuff like that. Okay. And we don't need that. Values of types. I'm not actually sure what we do here. Okay, so we switch on the fun. By the way, I'm gonna, I saw that many times now. I'm just gonna do yogurt fun placeholder. and define that. I don't even know where, to be honest. Maybe here. Unit fun placeholder is that. Okay. And this is your fun builder is only used for compiling. So this also good. Ah, yeah, it belongs to this. Just got lost when I split this up. Okay. Yeah. Maybe running code at compile time. Some of one has the one guarantees that functions compile time non-args run at compile time. There is the code for that. I just think like every time I hit some key on it, not even then, something that flickers at the top of, but yeah, only in OBS. That's really weird. I don't know why. Well, that's super weird because it just cost the screen. Huh. Strange. Yeah, compiling code to run later. Yeah, if not all arguments to a function are known at compile time, the function is compiled into some code. It will run later at runtime. Okay, so these are two concerns here. Yeah, I was doing this placeholder thing. This doesn't explain why it's there. It just is a weak explanation of why it's okay that it's there. Yeah. When a function recursively calls itself, we don't want the compiler itself, and we don't want the compiler to get stuck in an infinite recursion. Compiling the function again and again. To prevent that, we insert a placeholder in the unit. This will be, it will be overwritten at the end of this function. It's okay to put it there because code that calls this function won't actually inspect the generated body, I think. Instead, it will only use the return type, which it calculates from the function signature, which it derives, calculates based on the function's signature. Okay. Yeah, so there was some other place exactly. Yeah, boom. For recursive types, want to get stuck in an infinite because for recursive types we don't want the compiler to get stuck in an infinite recursion, so we put a place holder in the yogurt. Yeah, and reasoning is not important here, I think. Okay. Amazing. You know, over time, I like this. You know, over time, all the concepts of the language, they get much clearer, and the code gets clearer as well, because you can really like encode assumptions that you made and encode and explain important things and explain design decisions. So I really like comments, by the way. Yeah, just tasteful comments that explain why things are the way that they are. And if something is like weird and I'm confused by that, I try to add comments there, or improve the code like that if that's possible. But I think when the compiler is working and it's done, I think I basically want to go through the entire compiler again and add comments, not everywhere, but in many places where I'm just, when I'm focused on getting something done, I'm not taking the time to comment something, even though there's something, some background information that's worthy commenting. Yeah. All right. Let me maybe. Where was I? Like, running code, right? Running code. Yeah. So we don't need to. We don't want to put anything into the yogurt. Any compiled function. So we don't need to compute a signature. Maybe we do later on. Yeah, for detecting recursive calls. But yeah, for now not. For now not really. Okay, so the only thing we really need to do is switch on the function. And this won't actually, return a function that we then put in a map. But this will just return some value, hopefully. So running code at compile time. Now let's maybe print, we print something for compiling a function. Yeah, compiling signature. Yeah, okay, you know what? We do, let's do that with the recursive thing directly. So this would be this. Yeah. So, param types. Yeah, these are the same. The signature is the same. Yeah, we don't do any like yogurt.funds.something. No. We don't care about that. Yeah, to do catch recursive calls. Yeah. But that's just a to do for now. I think that's fine. And this is actually running that signature. Oh, hang on, but we actually want to print the values directly, I think. And it's not really a signature if you think about it. Yeah, let's not. Yeah, sure. let's just print, you know, the name and the arguments. Running name and args. Okay. And deal with recursive stuff later. So we look at the egg farm. If that's some code, then we do something. If that's a built-in, we do other stuff. We basically want to run the built-in, and yeah, that function doesn't exist yet. Fair. Where are my values? I had some values. I think they are still in my clipboard. That's nice. So yeah, we don't need some function builder or a compiler. No. No. No, we don't. We only need don't need yogurt IDs and push them somewhere. Oh yeah, yogurt values. Yeah, let's maybe put this in here, you know. Okay. Okay. Eggfun.impl. We have some code. We build values. And basically for every argument that we get, oh, hang on, no, we do something very similar to this actually. We zip stuff. We zip the code, yeah, body, params, which is some egg IDs. We zip those with the actual values. So we get the egg ID and the value. And then we add those to the values. Simple. Yeah, let's inline that. And yeah. Okay. And then we don't compile the body, but we run the body. Yeah. Using some params, maybe. I'm not sure actually. Using the args, right? Yeah. And we don't need a builder, we don't need a compiler, just run that. And then it has some result. The yogurt Comptime result. Yeah, and this is a big to-do, I would say. At least for now. To-do. Or maybe we don't even need that, because I think maybe functions should be analyzed in isolation. That also makes sense. If you call some function list 1, 2, 3, the list of int should have been analyzed before. But then I'm not sure. Maybe, yeah, I think yeah, okay, we probably need this. Okay, but still, let's add these other run functions. So we have, this will be similar. Let me just copy this compile thingy, the run thing will be super small. Like compared to compiling function, just running that is gonna be simple. So this will be a lot of trimming code down and simplifying code, and I like that a lot. Damn, almost 2,000 lines. That's crazy. Okay, so compile. No, this is gonna be run an egg body with some args, which are actual values. And the way we do that is we don't need a builder or compiler or something. We just run that body. Doesn't the API doesn't get much simpler than that. This returns a Hubert body Comptime result thingy. Okay, so Hubert doesn't match the number of args. Okay, yeah. And then we don't need, oh yeah, hang on. We do need basically the map of all values, body run. Oh, yeah, let's do that maybe. Let's just pass the values as a mutable map. Yeah. Map from egg ID to get a value. And yeah, we don't check anything here. We can just assume that the arguments to this body are in the values, because like we visit the egg, and every single egg ID that we have visited already is represented here. Yeah, so we don't need to build any args or something, instead, for each expression, we just compile that. Compiler code get that expression, that egg ID. And then we run that using the values. And that's just gonna, add some, I don't know, add some value there, probably. I do wonder how much code duplication there will be between running things and compiling things. I'm sure that the structure of that will be pretty similar, I think. But in practice, running things is a lot simpler. We don't need all these maps and code generation stuff and so on. But then again, you know, in stuff like the like a switch, for example, the condition is known at compile time. Yeah. Okay. But I think we still need to compile the other branches, you know, and see the types of those. Like, let's say some function that accepts an A, which is bool, and what it does is it switches on that A. I don't know, it switches, it calls not A, you know, to negate that bool, and then if that is true, it returns 2, otherwise I don't know, something. And now we call bar false. And the bool is just defined as, oh, it is actually defined up here somewhere, as true or false. Now what happens if there exists some function, you know, not using some foo of the type true, an enum type only containing the true variant? You could write something like this. Not saying that you should, or that is, you know, that this is best practice, but I think it would be kind of cursed that you know, if you have bar of some value, then if that value happens to be compile time known, that then the function may not compile, because then in here, you know, we say, okay, this compiles for the value true, and then we look for something. I mean, okay, this is value true type bool, okay, so that's not a problem. But then let's say that we actually save that. Let me do something like this. Yeah. This seems like it doesn't do anything, you know. But actually, if and this shouldn't do anything. You know, the type of loop should be the same as the type of A. Yeah, the type of A is bool. This is, you know, a Comptime known true of the type bool. Let's maybe print it like this. You know, like it's a true of the type bool. So we choose the true variant, but still we analyze all branches to find the common type and cast things as necessary so that this also is true of the type of bool. So that then down here we actually, you know, do function overloading for things of the type bool. So this function doesn't match because it only accepts, you know, stricter enum, but the other function, like the, you know, the real not function, that works, that matches. Because otherwise, you know, granted, like this is a very constructed example, but you can have these examples where something, you know, just something being compile time known makes the code that makes this not compile anymore. Like that's weird, and not because of some real reason, like it does infinite recursion and stuff. You know, that maybe like in those cases maybe we don't want to compile. But based on like things get overloaded differently, and that is not something we want to do, I think. So that means that, you know, even when just running functions with some compile time known values, we do kind of need to analyze all switch branches. Oh man, okay. Yeah, maybe to motivate this with a more, I don't know, reasonable example, maybe. Let's say we have something that is a list. Yeah, and then we switch on that list. So let's say this is an empty list. And we switch on that empty list. And if it's empty, we just return empty. If it's more containing an item and the rest, then we're actually gonna, I don't know, do something. Also return more of other stuff. So that this entire thing is also a list. We want the type of this to be list. List is not a full type, I'm just realizing. List of int, let's say. We want the type of list, oh yeah, even more important in this case, yeah. So we want the type of this to be list of int. If this returns, assuming this returns an int, like this is item, but I don't know, basically this is like, if the list is empty, then it just returns empty, otherwise it returns a list with only the first item of the list. Weird example, sure, but the type of that should still be list int instead of just empty. That's more powerful basically, because you have these extra type information things. And for example, then if you have some, I don't know, say blob map using something, not map, but yeah, I don't know. But the important thing is the return type of this should not change. If you call something with a runtime known value versus a compile time known value, the type of the returned thing should stay the same, except when you explicitly opt into Comptime stuff. So I was thinking maybe we should add some, like an explicit Comptime switch, maybe something like this. I don't know. Where we say, hey, this value has to be compile time known, and we want to switch on that at compile time, and then only the necessary, like the correct branch gets compiled. And we could use that to implement something like this parse JSON thing, where we really want to only compile the branch and not I don't know, crash somewhere in here, because we call target. In here we probably need to go, I'm not actually sure what we do here. Yeah, but anyways, if we do something like, hey, this, like we expect target to be a map in this case, to be a struct in here. Even, and we want to be able to call functions that expect some sort of struct. Or in here, we want to be able to call functions that expect an int. We want to be able to call, to say, hey, this is actually going to be int plus 1. Again, weird example, but anyways, the question is how do we do that? Because it seems to me like that requires an entire compiler, or at least something like that. Yeah, I mean, that's... I don't quite know what to do here, to be honest. That is weird. Super weird. Or we do just say, compile. Inside of the run function, I mean. You say, hey, please run this egg function with these arguments. And then we could basically do, hang on, basically do this. Yeah, do this, do the same thing as we do here. But instead of adding yogurt op params, we add yogurt op comptime values. Seems a bit hacky, to be honest. But I mean, all the comptime, all the built-in stuff would get much easier. You know what? It is pretty late, so I'm gonna sleep and think about that. But yeah, interesting. Okay, so I spent some time thinking about this, and I think I want to keep the compile time and runtime code separate. Yeah. Or at least, I want to not use the same entry point. But I may just basically calculate the egg fun. I take this code and copy that up here to the runtime code. But that's a lot of code. Yeah, here where we say we want to run this egg fun. Yeah, let's insert this here and then adjust that as necessary. So yeah, the first thing is finding out, replacements, like finding out recursive calls, and having this placeholder here and calling that placeholder and so on. And I don't have a problem with that. So that was fine before. So we also don't need a placeholder here, and we just need this, we switch on the function and do different stuff depending on that. I do think the code should be different than this. So let's maybe go into this in more detail. So here we create a yogurt fun builder, so we will actually build a function. but these parameters, they won't just be yogurt op params, but they will be yogurt op Comptime params of that type. And I think we can just take the args. Instead of the param types, we have args. And then both.b will be an argument, aka yogurt value. And we can convert that to an expression and push that. And that's the only difference, I think. That we still need the claimed return type and the actual return type, and we need to check that they are assignable to the other, and yeah, the return thing of the builder should be a Comptime value. Here the question is, what what is what if the function panics, for example? Yeah, that does not seem good. I don't like that. Okay. How about we have values, but also types of of expressions, of egg expressions. So we actually store the values and the types, and these will be plum types. And yeah, for each of the parameters, we put those into values, and we put their type into the types. So this will be both dot a, I think. Not actually sure. Probably. Types dot put dot a, yeah, that's the ID, and both dot b dot type. Yeah. And then we run this with information about the values and types. And yeah, these take values as well as types. So we compile the individual expressions, not with a builder and a compiler and so on, but just with the values. Oh, by the way, these should be mutable. Values and types. And this is going to return a yogurt Comptime result and not a body. So after we compiled all expressions, I think we actually want to return the last expression, maybe? Oh, yeah. Or I replaced this yogurt Comptime result with just a normal result. Yeah, I think that makes sense. Nested results. Oh god. Okay, so the outer result represents whether something, like whether there's a compiler error in here. And if there's no compiler error, then this is the result of the code when it would run. And that's either a concrete value or it panics with a string, because then we can use the question mark. But you know what? No, that's kind of cursed. That's kind of cursed. That does mean that we need to check in a lot of places, like, you know, if this is hang on, compiler.code.getEggID, we run that. If that is an error, then we return, and then that is a yogurt Comptime result. And yeah, let's implement the OR function for that yogurt Comptime result. So in Martinez, there's a built-in OR function that you can write for types, and it just accepts a single item, you know. And when you use the OR syntax, like foo or bar, this is control flow, because this is lazy OR, basically. So it first evaluates that foo, and then that foo can basically determine whether it should just short circuit and evaluates to some value, or whether the alternative here should also be evaluated. And yeah, the obvious case for this is bools, you know, where if you have true or something, even if that's a function call, like that something is not evaluated, because we already know that the entire thing will be true if there's a true here. Or for results, you can write result or and then a default value to basically, I guess, unwrap the result, something. And we want to do something very similar for yogurt Comptime results. We want to say that, you know, you can basically do, you know, we have some Comptime result, and then OR, and OR can also accept a binding. So either this is successful or it has a panic message. And then in here we can panic, or we return an error or something. Like we can do anything we want in here. And then this entire thing will just be a yogurt value. Because there would, like, yeah, okay. Let me just try to do that. So this will return a control flow, I think, of the short circuiting thing. So the yogurt value and the binding that is provided to the OR, which will be a string. Let's maybe sort these in most obvious order. So we switch on the result if it returns some value. Then we're just gonna return control flow dot short circuit of that value. And if that panics with some message, we're gonna return control flow evaluate alternative with that message, something like this. Yeah, and I think we need to put those here, because type inference is not particularly strong in Martinez. Okay. But that means that we can basically do this, you know. Either we just run this expression, and if that panics, then we say, hey, everything's okay, you know, the code did compile, but the result is that it panics. So you could Comptime result dot panics of that message. And yeah, that is kind of verbose, quite verbose actually. Yeah, I guess that's just what I'll have to deal with for now. And then last value maybe is going to be a yogurt value. And yeah, like in every cycle of the loop, basically we assign that value here. Oh, we don't even need to do that because we already add that value to this values map. So values dot put your id value, and types dot put value type, and then in here we know that the return value, like the return expression of the function, added a value in here. So we can just say, hey, we're done executing this body. The result is values.get of the return value. Amazing. Yeah, that is amazing. Okay, and here we calculate some ID apparently. And then we probably do something with the ID. We push that to the body and other stuff. Okay, we don't actually need to do that. We'll just do something, I don't know, let's say value, I guess. Yeah. So we switch on the expression kind. If that's a param, that's unreachable. If it's an int, then it's just a yogurt value int. If it's a string, it's a yogurt value string. If it's a symbol, then it's a yogurt value symbol. Okay. If it's a struct, then, well, we know all the fields, you know, like we know the fields are yogurt values. And we don't need to check, like, are all fields Comptime? In that case, you know, we build a yogurt value struct of these Comptime fields. No, we can just say just return those fields. Let me see, fields is something to yogurt value, and types don't really matter. And then in here we just say values.get, I think. Value. Yeah. I mean, really it's just, you know, field. Why do we need the type? Oh, because of hang on, there's a yogurt value. Is there a yogurt value struct? Nope, only string. I think there should be a yogurt value struct as well. Yogurt value struct. With some fields, which is a map from the field name to the yogurt value, and that returns a yogurt value kind.struct with those fields, and then we have the type. And the type, well, we take the fields, so this will be field types. We need to build those. It's going to be a map from string to yogurt to plum to string to type, and then for each field we're going to add its type to this map. Yeah, and then the entire type of this thingy will be the plum type.struct of those field types. Yeah, much better. And then in here we can just say, hey, we want to create a struct, no problem. Let's gather up all the fields. Yeah, for each field in the struct, we're going to get the value from the values map. And we're going to put that value in this thing. Then we don't need the plum type struct. Instead, we can just return the value directly. So there's going to be a yogurt value struct of those fields. Boom. That's pretty simple. That is super simple. And then we have members. Okay, so for members, we look at the auth value. Yeah, the type. Oh, extending the type. That actually makes sense. Yeah, we need to do that. True. Yeah, and that's supposed to be a struct. Sure. Type, and then these are the auth fields, or the types of those fields at least. Let's maybe rename that to something reasonable. And then we get the field type, or the type of this expression, I guess. And yeah, this is going to be Comptime known. So this is just that. And nothing needs to be pushed in here. The struct just immediately has, oh, hang on. The field already contains the type. So we don't need to, get the type in here. We can just say that. Damn. That is cool. Yeah. Instead of this, I'm going to, I think this unwrap with a message. Yeah. Expect to get member on non-struct. That's one error case I want to handle. And the other is if the member doesn't exist. Okay, maybe something but unwrap member. Yeah, okay. Cool. So then, this now is the interesting part, a switch. We know the condition, so this is, values, lookup. Amazing. Yeah, well, values.get, yeah. And the condition expression, no, that's not something that we need to do. Not something that we need to do at all. Condition type is the type extended one level, sure. That is supposed to be, condition type, is that used? Yeah, that is used, okay. Yeah, I'm not sure about these ones actually. Probably makes sense to keep them in here. Yeah. And then for each case in the switch cases we do other stuff. Yeah, this is just gonna be condition.type. Okay, and then we lower all cases. That's the interesting part. We don't actually want to compile those cases though. Instead, we only want to find out the type of them. And I think we'll just have a separate function for that. Ooh, okay. Yeah. Yeah, basically a function find out type, or something like that. Yeah. Find out type of some expression, basically. Like similar to the run functions, we have these find out type functions. And we also need to be able to find out the type of a body. Not of a function, because that's clear using the signature. Yeah, but that's kind of, yeah. Okay, I guess. Find out type. Okay. Hang on. What did I do? Okay, we have the run function for a function. We have the run function for a body. Let's actually group them together. We have the run function for an expression. We have the run function for a body again. No, these will be, we'll find out type of some body. And this will call find out type of some expression. Okay. Yeah, and essentially for each expression in the body, we don't need, oh, what's this? Oh no. We don't need to find out the value, we just want to find out the type. So yeah, this will just be compiler code get ID dot find out type. Amazing. And this should not depend on, may depend on values, because there may be like Comptime switches in there. Oh shit, this is getting complicated after all. When something panics, we still need the type of the entire thing, right? I think so. Find out type. This is kind of ugly. I don't like that we have basically duplicated code between compile time, you're running some code at compile time versus compiling that code to something. And when compiling code, we also do optimizations for the, you know, I guess for the for what do we do optimizations? For Comptime things. Like if you just compile code, but one of the expressions is a 3 and the other is a 2, and then you add them, that should be a compile time value 5. So even if we compile code, we actually do runtime evaluation, like a compile time evaluation of if all dependencies of some expressions are known at compile time. So this is definitely intermingled. These two stages, they are intermingled. That's just a fact, I guess. And that the entire logic and errors and so on, that, like we want consistent error messages, you know, regardless of whether some code runs at compile time or runtime. And I don't see that working out here. I just don't see that. Which really sucks. I think I'm just gonna remove all of this until, I don't know, somewhere, you know, find out type. Yeah. Or at least, you know, I'm gonna put that into the temporary file, but no, not the way to go, I think. Which is really, really sad. But what are you going to do, right? So I guess let's maybe look at our Comptime cast value, doesn't it? Okay, that's this. Definitely belongs to up to the runtime code. Yeah, compile time code. Man, these names. This file is pretty long already. Hang on. We do the lookup. Okay, I'm fine with that. We have several constructors basically. Then run code at compile time. I'm gonna put that in here, the compile time cast. And then I had assumed that there's also a section for your compile code at compile time here. Weird that the compile cast that the compile function is up here. That's really weird. I think this entire file is just very messy right now. But okay. Running code at compile time. Yeah, and actually this will, yeah, I mean this will just delegate to the compile time, you know, to running like compile on things. So let's just copy that, I guess. So this one right here. Kind of sucks, but okay. So in here, if we have some code, we actually compile that function, even if we just want the runtime value. So we create a compiler, we do all that stuff. We zip the body parameters with arguments, and these will be Comptime parameters. And we push them to some things, and then we actually compile the body. And yeah, that last expression in there. Yeah, that should either be a Comptime value or it should be a panic, I think. Like do we have a panic expression? I hope we do. If not, we're gonna realize that when we have code that panics at compile time. Yeah, but this is the only allowed case. You know, in the default case, like that's you know, Comptime call results in runtime result And then we have body.returns, well, something like that. And not this. Okay, so by default we just panic. And then we push some cast in here. Oh. If it's a Comptime thing, then we actually do a Comptime cast. Yeah, that's correct. But we don't want this to be a Comptime operation, but instead just a value. And this is a switch, so there will be no then. Yeah, we don't need to push that to some builder, because we don't even have a builder in here. Oh, we do have a builder. Yeah, fun builder, which is the, oh yeah, the return type of the builder, basically. But we don't use that. Yeah, no. Cast fun, we don't use that as well, because that's only for runtime casts. So instead we just have a value, basically. Yeah, and let's maybe get that, like pull out that switch first. Yeah. And panics. Okay, and then we do that like this. And then at some point we want to return that value. Okay, so what we actually do here is we return some yogurt Comptime result. Okay, which either returns or panics. That's fine. This, we don't use that yet, so let's maybe uncomment that and comment that out and maybe use that later. Although maybe it's a bit unintuitive. We don't have to check that. We could just do is assignable to, because the type is assignable to itself. Oh yeah, this is only for, you know, conditionally compiling a cast function and so on. And yeah, in our case, that's just not something that we need to worry about. Okay. Okay. Yeah. And what else? Get recursive calls, that makes sense. Yeah. We have a Comptime cast, that makes sense. And we also need a built-in .run for concrete args. And we're gonna add that here. So run some built-in for some args, which will be a slice of yogurt values, and that's just gonna return a yogurt value. I hope. Also egg and yogurt. Yeah, no, we don't need that. Captured variables. I feel like this is probably, yeah, it's defined down here as well. That's just, I think that was just copied to the top because something. You would bodybuilder as well, and then compile. Okay, hang on. What do we have up here? We have the captured variables, collect captured, you would bodybuilder, and then a compile function for built-ins. Compile built-in, hang on, but this is that same compile function as down here. Comptime cast, we have that as well down here still. Why is there so much duplicate code? That doesn't make any sense. Okay. Okay, yeah, compiling a built-in is just for runtime known parameters. There is no funny business going on here. Sure. I mean, this could just be, you know, we can just evaluate here that because this entire thing is wrapped in an OK. Yeah. Okay. But this is entirely runtime stuff. That makes sense. And then above that we have, maybe let's fold these functions in. You compile this, compile that. And let's, I think, yeah, having a like an overview of the functions defined in this file. You know what, I'm just going to go through the file. Apart from this egg fun at the top and this constructor stuff, you're running code at compile time. And this is basically where this starts. Let's get an overview of for to run at runtime. Okay. Yeah, let's add this. Let's move this to the top because that's basically the entry point to the compilation. Well, let's maybe move that way up to the top. Or not. Also, these are kind of just yogurt constructor functions. Yeah, so I'm gonna move all of this as well as this. Oh, maybe this. It's more like an internally used thing in here. I'm gonna move these constructor-like things into the yogurt file where they belong. Okay. So we have, looking up functions in the egg. Sure. We have a yogurt fun placeholder. Okay, I am gonna move that over here. Yeah, and let's actually move this to the entire top. Okay. Okay. Oh man. Okay, so we can convert egg to yogurt. And first we have functions for looking up functions in the egg. Sure. Then we have code for running code at compile time. Yeah, let's move that to this garbage, dumpster file. Yeah, running code at compile time. These are the kind of run functions, But also, apparently, these compile functions, which don't make any sense to me. Compile cast fun body. And that's something that exists further down somewhere. Yeah. I mean, we have two sections in this file, running code at compile time and compiling code to run at runtime. It's kind of the opposite, Running code at compile time and compiling code for runtime. Yeah. And these functions down here, they're the typical ones, like we have all these compile functions, compile this function, compile this body, compile this expression. We also need this, what are the captured variables of something, as well as I guess compiling a built-in function for some types. Yeah, makes sense. And compiling cast functions and so on. Okay, so this is all runtime stuff. But then up here, we also have these. That doesn't make any sense. In here we don't want any compile functions, but only run functions. Well, Comptime cast also makes sense. So we want to be able to run some function at compile time. We want to be able to run some built-in for some concrete values. We want to be able to not do this. This doesn't make any sense. And the code for that doesn't even include the, let's just remove that. So let's remove these compile functions here. Okay. Great. So running a built-in at compile time. We had some handling code for that in the previous code where these two stages were kind of intermingled. So let's copy that out and then simplify that a lot. I think that was kind of, this code right here. There were, but I'm just gonna copy that off GitHub. Compiler, egg to yogurt. Oh, they still haven't pushed my changes. Well, I guess. Fun to yogurt of some built-in. Hang on. Oh, I have pushed that. Okay. To yogurt of some built-in, yeah. And this part in here, especially. I'm just gonna copy all of that. Amazing. And I'm gonna paste that in here, and we're gonna radically simplify that. Did I copy the entire? Yeah, I did copy the entire function. Okay. Returns a result of yogurt thingy and string. I think this is not representing panic, but a actually show. Okay, so yeah, we don't have any arguments, any params, so we just have args everywhere. So let's rename this to args. And then let's simplify this code. So these are concrete yielded values. So we can, these, we don't need to get some values in here. We don't need to emit any instructions for doing things at runtime. Instead, we just evaluate to an ID, to a result of some value, not an ID, so we don't need to push anything. This is just going to be yielded value int. Boom. Okay. Yeah, and these are both ints, so let's actually do that. I'm going to do that here. Getting the specific int values. And then we just push the yogurt value that is a plus b. Okay. Yeah, this seems very cool. And that we do the same thing for subtracting ints. Except this time, I'm gonna use a minus. And the same thing for multiplying ints. I think this really shows how, if that compile time and runtime handling code is intermingled, things get really complicated. But if you only separate out, hey, if you basically switch further up in the compiler, hey, are we at compile time or runtime? If everything is compile time known, then we're just gonna give the values directly. The code becomes pretty straightforward. And the other code, like compiling a built-in, is also pretty straightforward, which is down here. Not as straightforward maybe, but still, you're always just pushing an instruction. But if you intermingle these two concerns, then you have this, always have these checks. Hey, if this is Comptime known and this is Comptime known, then please do something completely different from, otherwise emit this instruction. So handling these special cases at a higher level in the compiler makes the code cleaner in this case. Okay, so multiplying values, dividing values. Oh, we don't handle if b is 0. Just realizing that. Should maybe do that. I'm gonna add a to do in here. Handle b in 0. And same for mod, by the way. Yeah. Then ending ints. Yeah, it just means and. Okay, same for or. Oh, where we use an explicit OR function, sure, an XOR with this one, and compare is interesting. Okay, so let's maybe first do OR and XOR. This used explicit OR function. This one uses the XOR symbol. Yeah. And then we compare to integers. And yeah, we know these are both integers. These are both Comptime known. and we just compare A and B. If A is less than, oh yeah, okay, we do need that, I guess, because only that is indented. And then, yeah, we could call that Comptime cast of type ordering. Create a symbol that has the type, symbol less, or type enum with only greater variant, and then we cast that to the more generic enum variant, because you shouldn't depend on that specific type. Amazing. Amazing. Okay, yeah, the okay thing, it's kind of like the default. So and we do wrap everything in okay. So let's not actually use this, I guess. Just create values directly. Okay, then strings. Yeah, these are both compile time known strings. And what we do is we just concatenate those strings. Okay, now this is interesting, because this shouldn't just return a yogurt value. This should return a string, because it panics. Oh. Okay, so now the question is that string a compiler error? We are probably calling crash in a few places with a compile time known string, and that shouldn't be a compiler error. Because it should only, it's fair to write that in your code, because it will only crash if it reaches that crash. Yeah, so this is going to have to be the result of a result, which I don't like, but yeah. Let's maybe turn this into like the value is something, and then down here we can just say okay of the value. Oh man, the boilerplate. Okay, yeah, so or we can say, I mean, we could also just define an enum, built-in result, which is either a value that returns a yogurt value, or runtime crash. I think it's called crash, not panic, by the way. Well, you need to deal with that. Okay, so runtime crash with some string, or it's a Comptime compile error. And with some string in here, but later on this would be like a full-blown error. Yeah, and this returns just a built-in result. Which means we can actually format that on a single file, a single line. And down here we just say built-in result returns, and in here we do an early return of return built-in result dot runtime crash of that message. We should also have a type in here, I think. Runtime crash. Yeah. Because the code after that, you know, still needs to like do type overloading and stuff like that. So either a runtime crash or a compile error. It's called Comptime error actually, because this is runtime, this is Comptime. Yeah. Okay. Runtime crash, which will be a tuple and the type never. Because for the crash function, you should be able to depend on this returning never. Yeah, this is known to be a string. Amazing. And then in here we had some to-dos. Yeah, we can actually handle those. So if e equals 0, then we just immediately return a built-in result.runtime crash of divide by 0, and that's going to be the type int for, you know, further type inference and stuff like that. And we can handle that same thing in here. Let's call it mod by 0. Okay, yeah, now things are getting, you know, where they are supposed to be, I think. So type of, oh, that's interesting. Type of with a runtime known value. That returns a type with a Comptime known value. Okay, yeah. And somewhere else we need to like handle the case of calling type of with a runtime known value. We kind of need to special case that or something. I'm not entirely sure, but yeah. Type info is just or args.get. That is always a Comptime thing. That's not even, you know, that's not even this. The message was kind of useful though. I'm wondering, in the other case of compiling a built-in, what do we do there? Yeah, here we use that. Okay, amazing. That's exactly what I was hoping. Okay, so we can remove that up here. And yeah, we know that's a type. So then, yeah, we don't push anything. Type info is the type of that. Right. Yeah. Yeah, but the entire type should be that. So let's maybe like Comptime cost type info. Okay. Yeah, I think that's fine. And not just fine, actually pretty cool. Yeah, this is going to be a struct of that field, yeah. nesting here. Oh yeah, yogurt value list accepts a type. Yeah, okay, that probably makes sense. Yeah. Okay. Yep. Actually, I am going to simplify this into yogurt value struct, followed by casting that to the type field. Yeah. Or even offering yogurt value struct with a type as an extra, parameter. Because for structs, I think that's quite a common thing to do. Yogurt value struct with type and fields. And we can assert that all fields have the correct type. Let's do that. Field.type equals type, or panic field has type. I don't know. And then in here we just do this part basically. Struct value kind. Oh, hang on. Yeah, field dot type. True. Field dot value dot type equals type dot struct dot unwrap dot get field dot key. Oh man. Yeah, that's for the simple assertion. Yeah, sure. Yeah, there's just that. Okay. Yeah. And that means you can just create yogurt value struct of the type field with this map inside. That's pretty cool, right? Yogurt value kind on variant. Why don't I have a constructor for that? I should have a constructor for that. Let's add a constructor for that. Yogurt value variant with a symbol, which is a string, and then payloads, which will be a slice of yogurt values. And that's actually just going to be this. Yogurt variant value. Of that symbol and of those payloads. Payload types, and figure them out. These are types, and for each payload and payloads, we add the corresponding types to this. Okay, So here we create a variant, and then we create some type. The type of that is plum type dot enum, actually. Yeah. Which expects a map that maps enum variants, in this case only one variant called the symbol, to the payload types. Okay, try to create this with that. Oh, this is a list, not a slice. So sure. Yogurt value variant. So this can just be a yogurt value variant struct. Huh. And then come the payloads, which is a list containing a single element, which is the list of all items. That list converted to a slice, and that's it. That's cool. Ooh. And then we'll do something similar for the enum, I think. Yeah. And look, this is pretty long, you know. This is just going to be a yogurt value variant of enum, and the payloads will be this list with the turquoise one to slice. Yeah, go. And the individual variants, they will actually be a yogurt value struct of the type. Let me see. You know what? We do a cast afterwards, anyways. So all these things in here, they don't really matter. We don't need this, which is pretty amazing. But you know, yogurt value list. Yeah. So this can just be a struct containing a name and args. Okay, yeah. Something up here is not working, apparently. Running arguments, args. Yeah. Okay, now we're basically back to, you know, going through the errors and figuring out where things are wrong. Okay, this call doesn't work apparently because yogurt op does not implement the print thing, the write function. But it does implement write debug because every value does. In here we call built-in.run, can only be used on results. It's a built-in result. Well, that's true. Yeah. So we need to switch on that actually and translate that to something reasonable. So this either returns some value, in which case we are just going to return everything worked. Yogurt Comptime results dot returns. yeah, yogurt Comptime result, and arrow of yogurt Comptime result dot returns of that value. Amazing. Yeah, if there's a runtime crash supposed to happen, with this message and type, by the way, not a problem. We can just return yogurt Comptime result error of this, and this probably needs, yeah, this does need a runtime. Let's call it runtime crash, because I think panic is in concept. I named this panic. In Plum, I want to name that crash, because that's, I think, a much more intuitive name for that. Your program just crashes. Simple. Runtime crash. So let's say this is also a tuple of, you know, some message and a type. Cool. Very cool. Yeah, so this will actually be like a crash, like runtime crash of that crash, and the crash contains, you know, the message and the type. There's a third case that we don't handle that yet, and I'm wondering why we don't need to handle that here. I mean, it's probably gonna, the compiler is probably going to yell at us later on. But first, let's fix these errors. Where's that error? Here. Switch ran. Okay, so either it returns something, or it is a runtime crash with a crash. Compile crash dot a, I think, was the string. Yeah. Okay, then up here there's the next error. Exactly, we don't handle case compile error. And yeah, here we need to return error, which is kind of not the way I think about this. Usually, like, you got the Comptime result. Hang on. This is a result, and we probably used let's do that. Yeah, let's use a very similar thing in here, I think. Let's just say this is a yogurt Comptime result, because it already contains a result in the name as well, you know, so. And maybe we can even use that. We use this, hang on, either value or crash or an error. Yeah, that's perfect actually. Let's unify that. Yeah, this is a Comptime. Right now I'm not too not I don't know the right word, too German penibel, I don't know, about the prefix naming with the yogurt in front. Well, anyway. Yeah, yogurt Comptime result is what we actually want. And let's just call it Comptime result. Yeah. This is pretty beautiful already. expected case expression. I mean, there's a nested switch that's very cursed anyways, so... oh, I see why. Yeah, if there's a Comptime error, we actually want to... Oh, hang on. No, we just want to return that directly. That is so beautiful. Yeah. Let's move the cast down. Yeah, down here. Then we have the run functions together and the cast as some sort of helper function. I think that makes sense. Really cool. And these are not built-in results, but Comptime results. Amazing. Yeah. And now we should get an error where we call functions. Exactly. We call some function, and we know, hey, all arguments are compile time known, so let's actually get the compile time known values of those. And then result.fun.run. Here we see that, oh yeah, this, yeah, we basically want to switch on that, right? Let's call it result. Oh, lookup result was already a thing. Which is, yeah. I think this is the better result thing. Yeah, so we switch on the result. If that function returns, we just push that value. If the function wants to crash at runtime, we also push something, but actually an instruction. So a yogurt op instruction crash, or like, and what does this expect again? Now it expects a type, so this would be crash.b. Hate that, but okay. Yogurt instruction. Yogurt op.instruction. A yogurt instruction, and that contains an actual instruction and the arguments. Okay. And the arguments are IDs, so we do need to basically push the string, push like a Comptime string. We crash with a message. So this would be yogurt value string of crash.a. And then we create a yogurt instruction, which contains an actual instruction, as well as the args, which will just be a slice of yogurt IDs. And the instruction will be instruction.crash. Okay, yeah. And then the third case, Comptime error with message. And in that case, we just want to return an error. And with the name of the function that is called. I mean, sure, why not? Return an error with that message and add this call. Amazing. So this call doesn't work. Okay. Push of yogurt fun builder and yogurt value. This has to be an expression, I assume. Yeah, that makes sense. Okay. So now there's an error up there. Right, so we compile the body, and that we switch on that. if that's okay, and we have some body stuff. If it's an error, if that didn't, oh yeah, see if that didn't compile even. Yeah, let's just do this, I guess. Or, if it's an error, then we actually directly return Comptime result dot Comptime error. Okay, so if we call a function with compile time known values, then the compiler will run that function at compile time. And if that function doesn't compile, for example, because we try to comptime switch on a value that is not, no, hang on. Yeah, I don't know, if for some reason that function doesn't compile, then this should result in a compile time error with some string. Interesting, yeah. Yeah, we don't really attribute that to the original source, but that's probably fine. Yeah, let's try to compile that and see where things break. Okay, so things don't work because there is no yogurt Comptime result. Like in here. Oh yeah, like in general, this should just return a Comptime result. No. Without any error attribution. Yeah, so this should just be Comptime result dot Comptime error of that string. Yeah. If this is a built-in function, previous to nothing. Oh. We get some value and then cast that value. So that would be Comptime result dot returns that cast value. How we do that? Let's switch this around maybe. I think that's a lot more sane. We compile the body, we extract the return value, and then we check that the return type matches that. And here we can just say, hey, value.type. And then let's also cast that in here. So we have all the casting stuff in one code block basically. Okay. No compiler errors, that's what? That's true. Like in general, the plum file is just a mess right now. Yeah, no, nothing of this makes any sense. Okay, I'm just interested in like what happens, Okay, so suddenly things happen. Some egg ID is not in the map when we say lookup. Interesting. let's maybe see at this. Oh yeah, so compiling main int, then we actually run functions at compile time. List 1, 2, 3, list that runs the list of 2 and 3 at compile time, that runs list of 3. And then in here we say, by the way, now we're compiling other functions. That is quite powerful. And that compiles built-in add ints, sure. Then we're done compiling that. We are done compiling plus. We are compiling map. Okay, and that doesn't work for some reason. Compiling map. ID 3 is not in the map. When we say lookup on some egg ID, so we compile the main function apparently, and it compiles the map function, which makes sense. Let's just look at the map function to get some context. The map function is defined in here. Yeah. Okay. Wait, this is probably I think we refactored how those bodies get their IDs. That the parent is responsible for adding those IDs. So I think that just didn't happen in this case. In switches basically. So when compiling a switch, is this run or does compile? Yeah, that's compile. Okay, in here we basically check that all cases are handled, sure. And then here we lower all cases. And what we do is if the condition expression is a compile time expression and its variant is the actual variant of the value that of the condition value that we switch over. Value, let's call it condition value maybe. If the actual condition value variant is the variant that we are currently compiling, then we want to do constant voting in there. So the actual variant.symbol is variant.key. I think in here we need to add mappings to this, yogurt to egg to yogurt ID thing. Oh yeah, because in the egg those have separate IDs. We can even see that. Hang on. Yeah, printing the egg reveals that in the egg, in the map function, we have these compile time values like 0 and 1 and so on. And we switch on that. And these egg IDs here, they should actually match some yogurt Comptime values. So what we do in here is we create the yogurt Comptime values. And here we say builder.push that payload value turned into a Comptime expression that is going to be one of the parameters of this. But then later on, when we refer to those in here, for example, and in here, we don't know what these to which yogurt expressions these egg IDs refer to. So in that case, we also need to add mappings between the egg and yogurt. And I think this will be pretty similar to how we compile yogurt functions, which will be up here somewhere. Yeah, compiling a yogurt function. Here we also build up these yogurt IDs, but then we add that mapping between that egg ID and yogurt ID. So I think we need to do something similar for the switch bodies. So, lambda condition, yeah, switch. Okay. Okay, here we have parameters, and yeah, this is a condition value. Oh yeah, regardless of whether these are Comptime values or runtime parameters. Like in the end, we have a list of IDs that has the same number of expected IDs of the body, basically. So in here, let's just add the mapping. So let's say, for each of the switch case params.iter, and the actual params, which are IDs.iter, we have the egg ID and the yogurt ID, and we just add a mapping between those. Yeah, something like this. And then the rest of the code will know how to resolve these IDs. And it works. Amazing. Yeah, compiling main int, and then running list 1 to 3, because that's compile time known. Damn, that's pretty cool. That is super cool. Hang on, like we can actually do arbitrary things at compile time, right? Let's say I have some Fibonacci function that expects an n, which is an int, and it returns an int, and basically it compares. Is there like a less than function? I don't know. N to 2, and if that's less, then it's going to return 1. Otherwise, it's going to return adding fib of n minus 1 and fib of n minus 2, something like this. Oh yeah, and we don't use that function. So let's also say that b is, I don't know, fib of 5, let's say. It's kind of sad that compiling the compiler takes so long. Yeah, is less than, maybe? Where do we deal with ints? We have bools, we have comparisons. Less than, there was a less than function. Yeah, okay, I guess. Yeah, less than n2, then we do some stuff. Oh, that does not look good. How did that start? If I can see that. No, I can't. I'm gonna try to start, like, really, end this really quickly. that was quick. Hopefully quick enough. Yes. Okay, so yeah, there's the egg. Beautiful. Super beautiful. Okay, running fib is less than 5.2. So this runs compare 5.2, that runs built-in compare ends. And apparently that was false, because this runs minus of 5 and 1, which runs sub. Okay, so now we run fib of 4. Amazing. Fib of 3, fib of 2, less than 2, no, then fib of 1, less than 1 and 2. Oh. Build and compare ints. And we continue down there. Oh, because we compile all switch branches. And if those values are compile time known, how do we even... So we need to adjust this basically. When compiling the switch branches, we have the parameters, yeah. I don't know how to deal with this, to be honest. Maybe we do need to... Well, yeah. So we see this percent. We know that this is always true, but to figure out the type of the entire thing, we still want to unify the types of both branches. So we just compile this branch, and well, we see that this is, we see that this is something Comptime known. So then we compile that for Comptime. We actually run that, even though this will never be chosen, and then we have this infinite loop, infinite recursion. Oh, that is painful. Okay, let's maybe... Let's only compile the necessary... Like if the condition expression is Comptime known, let's only compile that branch. I'm not sure if this is going to... Like, this may change the type of the entire thing. Maybe that's the point of that, getting more specific types. If that is kind of the point of Comptime, that we may of having these Comptime guarantees that the types may be more specific. And we may need some more specific types in cases. Let's try that. Let's just say that I don't like that, to be honest. But okay. Okay, if the condition expression is known at compile time with a condition value, then we get the actual variant. And then we compile that switch case thing. Yeah, basically this part right here. We kind of do this. And the condition expression is known at compile time. Then we get the corresponding case. That is cases. Switch dot cases dot get the case for that variant. Symbol. And then we compile only that case. And this will be, yeah, we don't go over all variants, we just compile that one single case. So we will build up the parameters, and because the value is compile time known, we can actually do this. We can say actual variant. Oh yeah, we have that. Never mind. Yeah, that is the key. And then we just say that. And we can immediately turn this into params also. Like so then we bind these parameters. We basically create compile time expressions for these parameters, and we bind those egg expressions to those. And then we compile that case using these Comptime known parameters. And then we do something like down here, add cast expressions when necessary. Yeah, that kind of defeats the point. We do this. Rather than pushing a switch, we actually just basically copy that body over into our surrounding body. So yeah, case.compile. Yeah, the case body is what we just called body in our case, like this. Oh, I see why that causes confusion. So let's just call this case body. Yeah, those params we already pushed. Yeah, we already pushed them. Oh, we only pushed builders. Oh, and never mind. Okay, that's fine. Yeah, we push the expressions to our body from that case body, and then whatever that case body returns is going to be what we return. Yeah. And otherwise, oh no, kind of messed up. Come on. Yeah, let's maybe copy this and undo some stuff, because that belongs further up in this thing. So this is the case if everything is compile time known. And here we really just want to insert that thing in our body. Hang on, I removed too much, I think. Okay, I'm gonna re-implement that. Okay. So we have our sanity checks. Actually I'm gonna add something new. If the condition is Comptime known, then we only compile the corresponding branch. Okay. Yeah, so we built the parameters and other stuff as well. The parameters will just be a list of yogurt IDs. We know this thingy is Comptime. We know the actual variant, that is our case symbol. And then for each payload, we're going to push that payload to our list of params. Okay, we add mappings for those, we compile the necessary branch, and then we add those parameters, we compile the corresponding body, and then we copy the content of that body over in our body. Otherwise, the condition of the switch is only known at runtime. Compile all branches is what happens here. So what we do is exactly this. It will be a bit simpler over time because we can simplify a lot of this code. So for example, here we check if the condition is Comptime. That's just never the case. and we do something similar down here again. There. But for now, yeah, we'll just go in the else condition, and let's see if that at least fixes this problem. Okay, yeah, this is some hex value. Maybe that's, I mean, that's probably correct, I think. I don't even know what this means. How we can calculate that. Hex, so there were 16 digits. This means 16, and then there's 0, 9, and then A is 10, B is 11, C, D, E is 14. So 16 plus 14 is 30. Is 30 a Fibonacci number? Maybe. I don't actually know. But it ends right as we expect this, That's pretty cool. 1e 10x1e in decimal. That's 30. Okay. So Fibonacci numbers. Not quite, I think. No, not really. That is unfortunate. Oh, hang on. No, we don't return the result of Fibonacci. We return. Oh, true. Yeah. We create this list and then we add that Fibonacci number to every item of the list, and then we get the sum of those. And okay, yeah, that's not. That's something different. Okay. And that's probably the lowest byte of that number. So. Adding 30 to each of these would be 96. 96. Yeah, 96 to hex is 60. Interesting. Okay. Yeah, I don't know what's going on there. Oh, hang on, the fifth Fibonacci number. Oh no, I need to calculate. Oh, you know what? Let's just simplify this and just say main returns Fibonacci of 10. And just run that and see what happens. Probably going to produce a lot of output. Okay, so 59, but this is hexadecimal. 89. I got examples. That's the Fibonacci number. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, we start with 1 and the first 110. Yeah, kind of. Yeah, it is a Fibonacci number at least. That is cool. Oh yeah, because we say less than rather than less than or equal to 2. Otherwise it would be 1 less. Okay, so that's cool. Let's maybe commit that. Yeah, not some assembly stuff, Rust. Ooh. No. Yes. No. Oh hell yeah, that's a lot of refactoring. Why is this? Yeah, refactor Comptime stuff. Amazing. And let's also, so one thing I want to do is catch recursive calls, you know, and also print the state of the compilation, so that you can, while it's compiling, we currently have these debug messages like compiling this function, compiling that function, and you see when that function is done. But I actually want to see like a tree of functions that are compiled, like basically see why functions are compiled, from which other functions are they reachable. And I think it makes sense to have some sort of context for that. So basically, to yogurt of egg, yeah, basically this compile function should accept some context. And this is like a compilation context, I guess, with a path, like a stack, I guess. Yeah, stack of the functions that we are currently compiling, basically. Yeah, so context of this stack. And I think the main compile function will actually expect a context in here. So let's get a context constructor that just returns a context with an empty stack. And then in here we can say, hey, let's create an empty context and return the address to that, because the context is mutable. So in here, all these functions, they also expect a context. And this will be just the context as some mutable thing. Yeah, for built-ins, we don't, like, these are not higher order in any kind, in any way, so these, I think there's not too much value in using the context there. They can't be recursive. Yeah, compiling cast. Yeah, I mean, that's probably fine. You would find builder, compile builder, and so on. Okay, and here we also want the context. Could just call it yogurt compiler and also have the egg and mutable yogurt in there, and then we wouldn't need to pass those around as extra things all the time. Yeah, we could do that. Yeah. And by the way, I'm gonna add a to-do in the switch, like to-do and simplify this branch as the condition is not Comptime. And by the way, I was hesitant to do this Comptime thing because I believe at some point I already tried this and it didn't work out. But maybe that was before I redesigned the type system. So yeah, I'm just gonna see if this works, and then yeah. So case lambda. Okay. At some point we should, yeah, here we pass in the, not even the lambda. I would have assumed that at some point we also use the egg and yogurt, and we have to kind of extract them from the compiler, but apparently not. Oh, we do, here. Egg and yogurt and so on. Yeah. let's maybe not do that. Like, I don't know. Call. Yeah. And here, like, this is a lot of extra stuff. Oh, maybe the compiler should just... What does the compiler contain exactly? Yogurt and egg. I mean, okay, you know what, let's say the context contains yogurt and egg. So a read-only egg and a mutable yogurt. And then to create a context, you actually need... Yeah, I'm gonna do that up here in mind. I'm creating some context of where the stack is just an empty list of strings, by the way, not stack. And yeah, we have the egg and the yogurt. Okay, and yeah, we compile that. Yeah, compile should accept some context, and then we don't need these anymore. Just return the Comptime result. Okay. Yeah, yogurt code compiler. Yogurt code compiler. Yeah, it has egg and yogurt. I think this should just be a context. Yogurt code compiler, and also yogurt fun compiler was a separate concept if I remember correctly. No, not really. Interesting. Why not just name it yogurt compiler then? We have all these run functions. Okay, yeah, Comptime stuff. Oh, yogurt fun builder is what it was called. Okay, so yogurt fun builder and yogurt code compiler. I see. And this is an egg code. What's an egg code? Yeah, thanks. It's one concrete block of code, basically. Interesting. Do I want to do that? Yeah, I mean, let's merge these, you know, let's say this has some context. That's just a context. And yeah, that's basically it. And sure, that means that when creating such a yogurt code compiler, you just need to pass in the context that you get. It actually makes sense. And this will just be yogurt context dot yogurt. And this does context context.yogurt. And what did I remove? Egg and code. Yeah, no, egg and yogurt should be removed. Yogurt, egg, compiler, same here. Just have a context, and that's it. Hang on. True. Okay. So then compiler dot context dot yogurt dot compile cast fun. Yeah, I guess. Value.comptime cast to claim return type, and then this can just be true expression. I believe there are many other cases where we, like, I just need to go through this file basically and clean that up. Take the time to do that, and then things will be a lot more clear, I think. Yeah, compiling a built-in. Yeah, so let's maybe not do that, but instead so compile it for these parameters with this context. Egg body with some builders, sure. Always like that. And then for the built-ins, built-in. Yeah, this is just going to accept some context. Okay. Okay. I should somewhere document that, nesting of, like, we have this code compiler and the context and so on. But yeah. That's it. Interesting. Okay, I would have assumed that there are more changes needed, but okay. So there's some to do, yeah, catch recursive calls. And here we can basically, well, we can basically get this signature, I would say, of this run, and that's just the name for the args, and that's not like super beautiful, you know, because args is still in a list, so it has brackets around. But still, we can basically check on the context stack, is that same call there somewhere? So context.stack, and we can iterate over that, and if one of these entries is equal to our signature, then we just, you know, panic. Infinite recursion. Otherwise, we're going to add ourselves to that stack. Or our signature. And in the end, when everything is compiled and we have this nice value, or rather we have built some result. Let's do that here. Result is this. We have our Comptime result. Before returning that, we also remove, like we pop something from the context stack. Yeah, and we could also do the same for functions, basically. But yeah, then we don't need these placeholder functions anymore. Okay, done compiling main. That is pretty cool. Yeah. Also, like at random, at some random place, you know, in, I don't even know where, maybe here, let's say, let's just print the context. Which is just going to be a list of strings. Or not. Oh, it's a context, right. But stack should be a list of strings that we can print. I'm gonna zoom out a bit. And you can basically see the Fibonacci calculation doing its thing, you know. And basically see the stack. Like you can see, I don't know if you can see that, but Fibonacci of 10 calls Fibonacci of 9, calls Fibonacci of 8. That contain, in this case, it calls Fibonacci of 6, then 5, 4, 3, 2, 0, less than 0, 2, compare 0, 2, built-in compare ins of 0 and 2. So you basically have a stack of which function calls which other function. And yeah, that is pretty neat. Huh. Okay, so let's actually use the same stack, I think, for compile time values, compiling functions, so we don't need the placeholder function anymore. I think that's more elegant. So placeholder function, let's just remove that, and we'll see that we will probably, hopefully, yeah, yogurt fun placeholder. No. Yeah. Instead, let's say that when we compile a function, if that same function is already compiled, yeah, everything's fine. We don't need to do anything. Otherwise, though, we we check if we are on the stack. Yeah. So maybe I should add some methods to the context. Okay, contains is on stack. Some string and this expects a context, and maybe then also push to stack. It's a mutable context, and similarly pop from stack. Just accepts a context. Okay, so here we do context.stack.push that string. Here we do context.stack.pop, and I think we need to do explicit ampersands there. And checking if something is on the stack is basically what we do here. Yeah, we pop something and then we ignore the thing we've popped. And in here, if the entry is signature, then we just return true, otherwise false. And this is the string. Okay. Oh, I think there's actually a contains. Context.stack.contains string. Or maybe not. No, only for sets and maps and stuff. Oh, but we can iterate over that. That should work. Contains of some iter. Now it needs to be mutable, so yeah, sure. So this should work. Amazing. Okay. Yeah. Okay, so let's start with the runtime code, where we basically just check, what is our signature first, boom, and then basically for each, we check if context dot is on stack the signature, then we panic infinite Comptime recursion. Otherwise, we say context, which is already mutable, and push to stack of that signature. And then here we print the context, sure. And then let's do something very similar in when compiling code. Oh, and also adjust this to use pop from stack. Amazing. And then in here, compile an egg fun. Yeah. We also just, we get the types, sure. We build the signature. If that function is already contained, everything is fine. We're gonna see, do we already compile that signature? Then oh, we do need a placeholder here, don't we? Hang on, this returns a yogurt fun. Where's that actually used? Because you shouldn't really inspect that yogurt fun, should you? Main just compiles that function and doesn't use the return value. Okay. Here, yeah, this compiles a body, this is the definition, compiles a body, compiles a built-in definition, what was that? Some expression gets compiled, sure. a body gets compiled, a body, some expression. Here a function gets compiled. Oh, and we actually use that compiled function. What? Oh no, we don't. We just save that and don't do anything with that. Oh. Hang on, if on like the Comptime, then we do some stuff. If not, then yeah, we don't do anything with that. And we shouldn't, because we shouldn't depend on anything that, we should just depend on the publicly declared type signature of that function. We shouldn't need to do anything like look inside what the function did or something. Yeah. Oh, this is in, oh, there's a compile some built-in, okay. Oh yeah, compile built-in, sure. Okay, so let's say we change the compile thing of a function to not even return the function, but return nothing, I guess, or the signature, or something. Like, hang on, if there's a call, suddenly we need to do something with that result, right? Hang on. So we look for a function. That's the result. And then here we push a call. Oh, and we just recompute that signature. I mean, yeah. Let's say we just return the function signature after compiling a function. I think that's sane. So this returns a yogurt signature, actually. And if it's already on the stack, for compiling, then that's fine. Like, we can have functions that recursively call themselves, and we just return that signature because then we don't want to compile that function again. Yeah, and then we push that to the stack. We compile the function body in here, which takes quite a lot of time. And then we put that function into the map, and we pop that thingy from the stack. And then we'll just return the signature. That is the idea. Yeah, if context yogurt funds, if we have already compiled that function, then we just return the signature because everything is fine. Yeah. If we are currently compiling that function, that's also fine. Amazing. Hang on, what is this? Yogurt signature. Still? String? Still. Okay. Oh, yeah, we want to return that. So then we just return, okay, yogurt signature, error of signature. Oh, let's combine this using an OR. Well, okay. Then we'll just return that signature. Amazing. And then we push the signature string to the stack. Amazing. Whew. Okay. Yeah, no placeholder needed, basically. And this comment is also not needed. Yeah, no argument necessary for why this is okay to do, because this is pretty obvious code, I would say. Nice. So then down here, oh yeah, this should just be a yogurt signature, sure. Yeah, maybe I should like add some compile function for code. Maybe. Down here, something is also going wrong. Oh, compile cast function. We want to do the same thing, and that means that we need context. No, and usually this is in the end, like I think there's context.yogurt. No, fun contains signature, then return signature. Yeah. If context dot is on stack signature. Hang on. Then return that signature. Amazing. Yeah, this is just, yeah. Okay, so when casting recursive types, we don't want the compiler to get stuck in an infinite recursion. That is true. But we don't need to put a placeholder in here because that's like really explicitly handled up here. Yeah, and this is just, you know, compile cast fun body from to body param and context. Cast from body from to build up param and context. And this will just do a compile cast fun with that same context. Amazing. So we do need to push that to the context here as well. So the context dot what is it, like context dot start compiling, or like and a push to stack, yeah, and push to stack. Well, the signature, and down here we say context dot pop from stack. Cool. Cast fun. Doesn't need a yogurt, no, but instead just the context. Like this. And same here. Amazing. So rather than printing the context every time, let's first remove the compiling something calls. Yeah, compiling signature. And you're done compiling signature, as well as running stuff. And instead, let's say that each time you push something to the context, that actually gets printed. And when you pop something, well, yeah, not. Yeah, we push something here. So let's say for, well, we want indentation and at the front. So for each standard error, we'll just print, let's say one space, and then we print the string directly. Oh yeah, and this is like 0 to context stack len. And that should basically print sort of like a tree of compilation. Do we still have the context thing in here? Yeah, we do. Let's remove that. Damn. Okay, so now you can really see why functions get compiled. And you can basically watch the compiler compiling stuff. You can see, that we compile main of int, and that means we compile Fibonacci of 10. That means we compile less than of 10 and 2. That means we compile compare of 10 and 2, and that means we compile built-in compare ints of 10 and 2. And then, that's basically the less than thing. And then we compile the minus function with 10 and 1, and that compiles the sub-ints and so on. And I think down here, oh, that's basically it. Yeah, it's just all calls. That's pretty cool. Wow. Let's do this a bit, make this a bit more beautiful, right? So let's maybe say that first I want to indent 2 spaces just to see how that looks. And the yogurt signature currently is only, well, we want to use the signature for both compile time running functions as well as compiled functions. So both for plum types as well as plum yogurt values, I guess. So we also want to be able to get a yogurt signature for a function with args. Like this is a slice of yogurt values. Here we basically want to put those args in the string. And then in here, we should be able to use that. Yeah, so yogurt signature of name and args. Yeah, because that's a yogurt signature, we also need to get the string. I mean, we could also, I think we should also just store signatures on the stack instead of strings. I think that's a bit cleaner. Yeah, look at that. All these function calls. We compile fib of 0, and that means we compile less than of 0 and 2. And we compile compare of 0 and 2, and so on. Crazy. Let's actually modify this function to not do Fibonacci, but do this list, and maybe here you use fib of 3 to get a bit more, a more interesting tree. Oh no. What's going on here? map of item and b doesn't exist. That is true. Let's just say this is the parameter to this function. Okay, so we compile main of int, and then first we compile Fibonacci of 3, that compiles less than, compare, built-in compare, and ultimately Fibonacci of 2, which compiles Fibonacci of 1, which compiles Fibonacci of 0, and Fibonacci of 1, and so on, and then we build a list of 1, 2, and 3. 3 at this point being the Comptime result of the Fibonacci call. That recursively calls the list of 2 and 3, that calls the list of 3, and then we add some things, apparently. Okay, but this is not compile time. Like these are actual ints, and then we call built-in, we compile built-in add-ins, and so on. Yeah, I like this. Some of these have concrete values, I guess, or concrete values as arguments, and others just have abstract types, but there's a clear separation between them. Yeah, let me maybe take a short break. Okay. Let's maybe first commit that. So yeah, no more function placeholder in here. Add context. Okay. Maybe we should rename that context to something, I don't know, something a bit more the stack kind of fits the context idea and the naming scheme, but the yogurt and egg that is contained in here is just random, basically. It feels a bit random. So I'm thinking about just naming this like yogurt compiler or something. And yeah. Yeah. So compilers. In the when compiling to yogurt, we monomorphize functions and we execute some functions at compile time, and we monomorphize. Let's call it specialize. I think that's a more commonly understood term. And we specialize generic functions for concrete types. Monomorphization. When doing that, we need to be careful about recursive functions. For Comptime execution, recursive calls result in a compile error. For compilation, for normal compilation, recursive calls are fine. Still, we need to keep, we need to detect recursive calls. So that the compiler itself doesn't get stuck in infinite recursion. Yeah. Okay, so we have this context. I'm gonna call it compiler. Yeah. Just yogurt compiler. And this context, at least in here, is going to be called compiler. I know that probably clashes with some other compiler down here. Hang on, where was that? Yeah, this yogurt fun builder. I think I'm actually going to map these, move these to the top as well. Yogurt compiler has this thing. The compiler's function run compiler stack. The stack is the stack of the compiler itself, running Comptime calls and specially containing the signatures of Comptime calls and monomorphized functions. And this will actually be, these will be yogurt signatures. And instead of calling these strings, we will also just call them signatures. Yes. And basically this is like a yogurt, I don't know, stack entry or something. Yeah, let's maybe also track like which of these are compilations and which are concrete Comptime executions. So we can, for example, highlight them differently in here. Yeah, so we know which are concrete calls and which are not. And also, like for if you have first class types, you know, if you have some function that accepts a t of the type, and you have another function that accepts like foo. Let me actually write that down. You know, we have some function foo that accepts some t of the type, and you have a foo that accepts an a which is an it. If we just say, okay, now we're currently compiling this, we don't know if this is a Comptime call to this one, or if this is a compilation of this one. So there may be conflicts, yeah, because types are first class. So it's actually not safe signatures in here, but yogurt, I don't know, stack entries, or like ongoing compilation, or I don't know. Stack entry is either here we are currently compiling this signature, or we are running this function, also a signature. Okay, yeah, and then we can also use more intuitive function names like push to stack will just be start compiling. And this will be compiler stack push or yogurt stack entry dot compiling that signature. And this will be stop like done compiling. And this can just be is currently compiling of that signature. That is pretty amazing. And that just checks if we have the corresponding compiling signature on here. And we're gonna do the same thing for running. So start running. Some Comptime thing. And then this will be running. Yeah, and here we look for whether the stack contains a running thing. Okay, yeah, and yeah, this is a bit boilerplate here, I guess, but I think having these like very differently named and specific functions makes the code down there, even more readable later on. Yeah, so yeah, creating a yogurt fun builder. I mean, sure, I would put that at the end, basically. First have the general like yogurt compiler that contains the compilation stack, as well as the egg and yogurt, the things like the global things basically. And then when inspecting some code, we actually contain like the parent compiler or the compiler or parent. Yeah, I guess parent. Not entirely satisfied with that. No. Okay, and we basically add some mapping. And I think a lot of the other calls down there should also be turned into like readable specific functions. That makes things a lot easier. Okay, so yeah, then we have a fun builder that we can create and get things from. That makes sense. Okay. So this is a lookup result. Result also clashed in some cases. Just the name result, So maybe this is the egg finding, maybe. Something that has been found. The egg needle, the needle in the haystack. Or egg looked up. Little, that's kind of a mouthful. Or just looked up fun. Matching fun. Oh, that's cool. Matching fun. Ooh, contains the function and the substitutions. Yeah. I like refactoring. Like things, some things get so much more readable, and just because of the naming and these simple things basically. Okay, so then we are at compile time running code, and here we can basically check, hey, we want to run this egg fun with these arguments. These are the substitutions. Do we actually use them? I don't think so. No. Of course we do. Yeah, for the okay. We need the substitutions to check the return value of this, and that makes sense. Yeah. Oh, hang on. Where we call run, we probably get that from from the matching fun, you know, from this lookup result. And in the other case, or is this the same? I don't know, yeah. So let's actually say, hey, this is just gonna, you know, run some matching fun, which also contains the substitutions. And I find kind of sad that we need the name in here just to build the signature. I think the egg fun should also contain the name directly. Oh, does the egg fun does contain the name? We don't need that here. And let's call this compiler. Yeah, you see this? How much better the signature gets. You just run some function that you found by matching for some looking for a function. That matching function with some arguments, and here's the compiler. Amazing. So the matching function has the underlying function, and that is the name, and that is the string. Yeah, and then we say, hey, compiler is currently running that signature. Hey compiler, are we currently running this function already? Then, boom, things are bad. To do, there should actually be a Comptime error. Like, you know, report the error instead of panic. And then in here we'll just say, hey, start running this signature. You just tell the compiler, hey, we are currently compiling this. That is great. That is super cool. And then down here we can actually say, hey, we're done running. We can even, the done running thing, yeah. We can say that pop thing, what we popped should be a yogurt stack entry. Yeah, and that should be running. So that should be running is sum. Or like, is sum, I guess. And we assert that. Yeah. Dot running. Oh, panic. Wasn't running something. Amazing. And yeah, do something similar when compiling. So assert that the popped thing is actually a compiling thing. Oh yeah, but we want to ignore the entire thing. No, that kind of can be it, but no, I guess. Okay. Yeah, more asserts, more safety. Beautiful. Yeah, this yogurt compiler here actually has a list of yogurt, what is it? Stack entry. Yogurt stack, that's very specific. Let's call it maybe yogurt compiling. Compiling or running. Yeah, so not really. Yeah, okay, I guess yogurt stack entry for. I don't really like that, but sure. Okay, so we have all that. we can run some matching function with some arguments, and it manually creates a yogurt code compiler using an empty map and some code. Let's add a constructor for that. Yogurt code compiler. Yeah. Just say code compiler, and we can call that on the original compiler. So on a compiler, which is a yogurt compiler, we can say, hey, now we want to run, now we want to compile this egg code. That's going to give us a yogurt code compiler. Yeah, where the other compiler is the parent, and the code is the code, and the egg to yogurt is an empty map from egg ID to yogurt ID, like this. Okay. Amazing. Yeah. Running this function. Oh yeah, and here we can just say, hey, compiler dot. Do we need the context in here? Not really. So compiler dot code compiler for this code. Nice. And then we have the params. Yeah, okay. And then we say code.body.compile. Using these params, using this builder, using this compiler. Otherwise, it's a compile time error. And then the value of that thing is something, okay. The claimed return type is, oh, the specialization can be done in the matching fun. Hang on. Matching fun, yeah. Let's actually say we have a function return type on a matching fun. That's just going to get the actual underlying function, take the return type on a match, I guess. Matching fun, match.fun.return type, specialize match.substitutions. We just want to call it match. But I think matching fun is a bit more descriptive. Yeah. Yeah, and this is going to return a type. Okay. So then in here we can just say fun, or like yeah, fun.return type. Should be the actual return type of the value. Actual return type dot is assignable to, yeah. Let me just inline this. I think that's, actual return type is such a long name, and claimed return type is also not something think this is fine, I think. And yeah, we're gonna cast that. Okay, yeah. I see that for claimed return type, maybe. Yeah, okay. And then it returns something. Fine. Context done running. Okay. Yeah, compiling a built-in, I think that's fine. That is pretty reasonable. This is quite long. Yeah, let's maybe break that on multiple lines. Sure. Type of is the yogurt value. Type info is this crazy thingy converted to a type info. And then Comptime cast of some value to some target type. Yeah, just because target is a bit more, you know, precise. Comptime cast lambdas. And then we have this compile thing. Oh, again, with an egg function substitutions, aka a matching fun. We don't need a name, we just need a context. I don't know. Nice. Yeah, so we first get the parameter types. And that's going to be fun.params. I mean, we could just say we have, fun.param types or something, similar to how we have return type. Let's do that. Yeah, return type, and we also have param types. Yeah, let's actually copy this code. So using a matching function, we can return a slice of plum types. That's called param types. Yeah, let's just say types, and in the end we just return types to slice. And this is the those parameter types specialized. Okay, matching fun, param types, return type. Just putting these things next to each other instead of somewhere splattered around this file already makes things a lot more readable. But where were we? Like, this was fine. I remember reading this. Yeah, this is not super beautiful, but it's fine. Comptime cast, okay. To the target, yeah. Hang on, is this something? Oh yeah, some of these yogurt value kind. We added constructors for all of these, so let's just say yogurt value kind dot something is probably gonna. Yeah, let's replace all of these with yogurt value struct in this case. Oh, never mind. We can't cast that struct because we are in the cast function. Yeah, and similarly here. Yeah, okay, that makes sense. But the other cases, yeah, in here, in this compile function, we can just say yogurt value struct, and then we don't need the type. If it's Comptime, then yogurt op Comptime. No, that's just going to be the struct. Of some type. Let's maybe Comptime cast that to the correct type, and then turn that into an expression. Yeah, something like this. Oh, evaluates to yogurt op. See. Yeah, let's adjust the formatting a bit, you know. We have this, or we have this. Yeah, that's cool. And then we don't need these. Sure. It's kind of like field values. Okay. There was some error reported up here. Oh yeah, we don't have a name. But we do have a fun. Matching fun. Fun.name.string. And parent types is just, well, fun.parent types. Nothing crazy there. And then we can say, hey, we have our compiler. And we can basically check. Yogurt.funs, yeah. We should add functions for these yogurt interactions, you know. Like, let's add. Now this is all stack stuff, this. And let's also add define and then some signature, and you can define a function. And that's really just gonna do, oh hang on, also needs a compiler, which is a mutable yogurt compiler. And then it just does compiler.funs.put signature fun, something like that. And we can also check is defined in this yogurt compiler. This signature. Turns a bool, and that's just compiler funs dot contains signature. Oh yeah, compiler dot yogurt dot funs. Even more indirection. Okay, yeah. What's going on here? We just say egg, hey, please look for this function. And then we say main.compile with a yogurt compiler of egg and yogurt. So that's the API that I want. I'm not sure if that exists. Nope, not really. So let's create that function. No yogurt compiler that takes an egg and the yogurt. Just returns the yogurt compiler using that egg and yogurt. Simple. Oh, and also the stack, an empty stack. So an empty list of yogurt stack entries. Okay. Yeah. Also, creating a yogurt should have a compiler. Should have a constructor. So let's add that as well. Just yogurt. Returns the yogurt. Yeah, let's infer that. A yogurt with an empty map, where the funds is an empty map. I don't want to type that out, so like this. And then we can just say yogurt is a yogurt. And then we compile that. That's pretty cool. Yeah, this is pretty, like, reasonably concise, I would say. Yeah. Okay, so what's not working? Why is it expected closing brace? Oh, I see. I want to get compiler errors here. Yes. Main.compile doesn't work. Matching fun and yogurt compiler. Oh, right, because the yogurt compiler needs to be passed as a reference. Perfect. And then in here we check, hey, yogurt is defined the signature, or compiler is currently compiling that signature. Like, this is so much more readable, you know, than looking like is on stack and something. And then we say compiler.start compiling that signature. As simple as that. And this is also weird. Let's just say name, and that returns a string. Name on the matching fun returns a string by getting match.fun.name.string. And yeah, let's just look for these kind of, yeah, I mean, yeah, here we can just do fun.name, and here as well. Not super reasonable, not super necessary, you know, to do that, but still, it's the small things. Yeah, and this will just be a switch on the fun implementation. Oh yeah, and this is just compiler.code compiler of that code. Build the parameters, which are all params, add mappings, and so on. Hang on, this is basically the same in both lists. Yeah, but I'm gonna leave it like this. That's fine. Okay. Yeah, there was some error somewhere here. We just do, where are we even? Compile some expression using this compiler. Unwrap. This is Comptime value. I do have to admit this is kind of this parallel structure here is kind of beautiful. Maybe I'm gonna remove the to expression after all. Anyways, compile cast fun just needs a yogurt compiler, which we are going to call compiler. Everywhere. Yeah, and we'll check that if the signature is defined or is currently compiling that. Signature. Otherwise we say, hey, we just start compiling this, and then in here we say done compiling. Compiler dot define maybe we could even merge these two calls, but like for values we don't register them, so it is would be kind of inconsistent, you know. Okay. So there's still an error here, compile cast fun, because this is called parent, I think. Maybe. Yeah. Oh yeah, no, don't create a new compiler, just do compiler dot parent dot code compiler of compiler.code. And then this actually defines a new function, so this would be compiler.parent.define. Yogurt fun. Oh yeah, and this is also like a reason why we don't want to tie that definition to starting and finishing a compilation between, because for lambdas we don't even register that we start compiling them, only for top level functions. Okay. So we could just say compiler.get. Here's some function, and then we get the return type. Yeah, let's do that. simple. Oh, it's a code compiler. Sure. Look up with a name and something. I missed that. Parent.egg. Egg.lookup. Oh, is that the type lookup thing? It is. Interesting. Okay, yeah. That doesn't work because, well, result is result.fun. Yeah, this is just basically that. And instead of calling this result, let's call this match. Or like fun even. Yeah, fun is such a natural term for a function. Yeah. And then we run that function. Amazing. And then we do stuff interesting. Oh yeah, otherwise we compile that function. And we get the return type. Just only is down here. And this returns a signature. Hang on. Amazing. Okay, so then we are, compiling function. We want to get the function return type. Yeah, sure. Fun name. Oh, hang on. No, fun name source. Actually, true. So compile cast fun. Compiler context. Context is not a field. Yeah, this is parent. Okay. You stack entries, they can't be compared. That is indeed true. So let's fix that. Oh man. Could name this match, you know. I think that's even more clear, actually. And similarly when compiling them. Okay. Nice. Yeah, I mean it looks the same, but the code is cleaner. Yeah, I wouldn't say that this was really like a refactoring, you know, it's more like cleaning up code, reorganizing code, and so on. Yeah. There's lots of tiny places where things get a little bit short, a bit more. The names are a bit more concise. The things are more readable. Like you'd say compiler is currently running, you know, instead of context.is on stack signature dot still. Like a lot of these tiny things, and they, you know, together they make the code a lot more readable. So maybe clean up code. Okay, so one last thing I want to do today is maybe, you know, in Zig there's this cool thing. Hang on. Yeah. So in my previous VM, which I think I don't have the newest version of, so I'm just gonna clone that real quick, and then I'm gonna make that. Or maybe not. Oh, is that a committed binary? What? Ooh. No, Zig build. Yeah, this is super cool. You know, that you can basically see live what the system is doing, what it's compiling, and you basically see progress in a hierarchy. So you can see what your compiler spends the time on and what parts of your build are slow. I think that's like, you could build like progress bars, but that doesn't really mean anything because you don't know how long it will take. You could build like just logs, but that will just quickly fill out everything. In Zig build, you know, when this finished running like it does currently, like that's like minimal. I really like the design of that. So I think there are some ANSI escape sequences, which allow you to basically move the cursor in the terminal, and I want to use that to you know, just play around with that to maybe achieve something similar like Zig does. Okay, so this looks pretty cool. So I can basically move the cursor up and down and so on. I can scroll up and down. What? That is crazy. I can even save the current cursor position. That's probably what they're doing, right? Saving the cursor position and then printing something and then restoring the cursor position, and then, you know, saving that again, printing something, maybe something like that. So I do something like this in Martinez. I'll just remove this because I figured out how things work. In Martinez, in the compiler, right at the beginning of the compiler, I have these ANSI escape sequence where we write the byte 27, and then when printing the status of something, we actually like move the cursor up one line and then erase the current line. So maybe we can do something similar in here. Do we do that directly in the active? I think. Yeah, I'm just gonna hardcode that here, and yeah, we can always like refactor things later. My usual technique of just building something and copying code and so on and cleaning up later. And for now, you know, until now, like so far it works out pretty well. Right. So yeah, I think for the compiler we basically want some sort of, you know, print status. And that's print status of the compiler. And yeah, we don't have any tooling mode or something. We're just going to do something very simple. Move the cursor up one line, erase the current line, and print. Let's just print a message like this. I'm not actually sure if this is a smart thing to do. Yeah. Like we want to erase the current line and then print the message and basically replace what has been written there before. I think that makes sense. Yeah, and we don't need the new line as well. Yeah, I don't know, something like this. But on the escape sequence. Oh yeah, that doesn't exist, of course. It's gonna be this. And when we start running, we're going to build a string, I guess. So print status. I don't quite know what to do here. Okay, you know what, let's just print for each. Even better. Let's run a little test program and then test in there, and yeah, not worry about integrating things with the rest of the compiler for now. Okay. I think something like this. Yeah. Let's say we have a mini compiler. And what we do is let's say we have a compiler with a stack, which is just a list of ints. Like a calculator, like a, no, I don't know, compiler. And we do, this accepts some compiler. Let's call it state, because it's like the state of the computation, you know. And we do state dot push vn. State dot stack dot push n. And the result is this. Except that we also need to pass in the state. And in the end we say state dot stack dot pop, and we return the result. Yeah. And here we do like state dot print. Not print, dot print status, I guess. Okay, and then in here we just call Fibonacci of 5 and state, where the state has a stack, which is an empty list of ints. And the status of this is just an ANSI escape sequence, erasing the current line, and then maybe, I don't know, stack dot last. Oh, state dot stack dot last. Yeah. And just to make this visible, there was no thing like waiting in Martinez, but we can just loop over 10,000 elements and just see what happens. So basically, we want to run the test.mar file. Iterating over float doesn't work. Oh, this is a float, that makes sense. Never, but this is an int, so we want to exit with 0, maybe. I don't know if that's correct. Oh, hang on a sec. Oh, interesting. 5, 4, 3, 2, 1. Yeah, I don't know. Maybe this is correct. So let's what was it like? Opening thing K, erase the current line. Is that anywhere here? Erase in a line. Oh, look at that. It's a K in here. So I think if we cursor horizontal absolute, moves the cursor to column N. Clear from cursor to the end of the line. Okay, that's probably what we're doing. This opening bracket for some reason, and then we should just be able to do horizontal absolute, so G, column N, default is 1, G. Let's just check, you know, in the Martinez compiler, there was 1A. Oh, up 1 line, hang on. Yeah. Okay, so I think I've figured out how these codes work. Okay, that's cool. Yeah, we want G, so 1G. Move cursor to front, erase the rest of the line, which is everything because the cursor is at the beginning. And it is 1. Okay. That seems fair. Let's maybe add a bit more in here. And like in the end, let's create a new line. Okay, so there was changing number. That is already pretty cool. What do we do now? Now I want to basically print the amount of, hang on, in the Zig compiler. What did they do exactly? Zig clear cache. Yeah. Okay, so the cursor is always at the beginning of this thing.
Okay. So probably they just track how many lines they printed, and then they move the cursor up that many previous lines. Moves cursor to the beginning of the line n lines up. Okay. Oh, but we could also just use this. Maybe. Let's try this. F is what it's called. So let's actually print the entire stack, So for each let's assume we're in a good position to print something, and now for each entry in the state stack, we want to print that. So we want to print that entry. And a new line. And then with this F thingy, we want to let me comment these out. Maybe. We want to be able to move the cursor state.stack.len entries up. It's kind of weird that I don't need a state for that. I can just pass around a list of ints directly. Just realizing that, don't need to overcomplicate things here. And just call that state stack. And instead of stack.stack, just use the stack directly. Okay. Yeah, and here we take the stack len and move the cursor this many lines up. So oh, this is pretty cool actually. This is super cool. What? Okay, but the lines below, they are still there. So I think we'll just have some max lines printed. Max len, let's say, for now. And before we print anything, we want to basically clear the lines. So we want to, do this. Right, ANSI escape sequence, move cursor to the front, boom, of where it currently is, erase the rest of the current line. Yeah. But we basically want to clear the maximum amount of lines that we have pre-printed below the current line, if that makes any sense. Where we basically want to move the cursor to the front of the current line and clear that line, and then move to the next line. So that would be
Next line, yeah. An E. Default is one line down. Move cursor to next line. And in the end, we want to move the cursor up again to the original position. So this just clears maxlen lines in the terminal, moves the cursor back to the top, and then we fill that cleared space with the entries, or at least with the entries, and we move the cursor up that many lines. And we also need to set maxlen to stack.len like that. Oh, and now it also becomes like less than that. Oh, that is pretty cool. Yeah, we should also print the status when we remove something. Just realizing that, because there's still something left at the end. That's pretty amazing. That is super amazing, actually. What? Okay, hang on, but hang on. Why did it remove the original? Usually these programs, they print this one here, compiled, and then running, and then below that is your cursor and your actually program output. But for some reason that doesn't happen here. For some reason it doesn't. Let's just print it for you a few lines at the beginning and see what exactly gets removed here. Foo and bar just gets removed. Interesting. Bar gets removed. Hang on. Why? Okay, in the beginning max lines is 0. So we just move the cursor to the front. Oh no, move the cursor this many lines up. Yeah, max len, okay, 0 lines up. Right. We push something to the stack, then we print the status. Yeah, max len is still 0 in that case. We move the cursor 0 lines up, which shouldn't do anything. And only then we print this. Stack len many lines. We move the cursor stack len many lines up again. That shouldn't remove, that shouldn't overwrite the existing line. Okay, I just want to clarify if this works with max len 0, because maybe this is weird, Let's maybe say we have foo, we have bar, and then we'll just move the cursor up and print bears. Okay. If I put a 0 in here explicitly, that gets removed. If I put a 1 in here, that also gets removed. Okay. 2. Now the foo was overwritten. Okay, so. Oh, hang on.
So yeah, if I put a 2 in there, that foo gets overwritten, but 0 and 1 behave the same. Probably because like the 1 is the minimum thing, so the you can't provide 0 in here. That actually makes sense. Okay. I can work with that. Let me maybe print or like create a few more helper functions. Move cursor to front. It just does on some writer. It just does writer.write ANSI escape sequence. Erase the rest of current line. Move the cursor to the next line. Move cursor to next. And this should also accept a number, like the n. And basically, only if n is larger than 0, then we want to write that. And same for moving the cursor to the previous. So if n is larger than 0, then we want to do that. Yeah. Okay, so I think that allows us to simplify this quite a bit. Or at least, make it more readable. Move cursor to front. Erase the rest of current line. Move cursor to next line. Move cursor up of max len. Move cursor to previous of max len. Move cursor to previous of stack len. Yeah, we should use that. That is pretty amazing. Oh, hang on. Hang on. Those lines didn't get cleared for some reason. What? Move cursor to next of 1, move cursor to previous. We output the exact same thing, don't we? I did too many changes in one go, I think. Okay, I have this. Yeah, okay. Let me just uncomment this and then... Okay, so this is the weird behavior that overrides this. Let me first see if I can fix that manually by doing something like if max len is larger than 0, then do this. And similarly here, if stack len is larger than 0. Yeah, that works perfectly. True, we don't really need the new line at the end. The extra new line. Yeah. Okay. Also that that it scrolls down. Yeah, this is super cool. Super cool. So now I want to use those other functions. Move cursor to front. Move cursor to front. And maybe also erase the rest of current line. See if this is still the same. No, apparently not. What? G and erase that rest of line. Should be K. Okay. Yeah, this is perfect. This is honestly perfect. And then move cursor to next line. And then in here we can just say move cursor to previous max line. Amazing. Okay, and this is also move cursor to previous of stack len. Okay. Nice. Cool. Now one last thing. Actually, let me print some of the numbers, repeatedly, like for I in, let's just say print like calculating. Yeah, sure. I think that's fine. Crazy. Colors. ANSI terminal colors. I want to use colors as well. Select graphic rendition subset. Make text red, bold, and underlined. Let's try that. How 33 octal. Yeah, that's the 27 I have in my code. This one. Okay, and then afterwards they have like the 27 and then an opening thing 31 1 for M. Red is 31 apparently, and then bold and underlined. And the last part just clears this. Okay, and M is apparently color stuff. Sure, let's try that. Like, standard error dot write ANSI escape sequence. That already prints the thingy. And then we do this. Red and bold. And then we also do the same thing for disabling, like resetting the color. Okay. So now these things should be red and bold and underlined. Crazy. This is amazing. Super amazing. What? Okay, so what else is there except red and bold and underlined? So bold is there, okay, that's the one. In particular, the foreground color, set foreground color. 31 to 37. See color table below. Okay, so 31 is red. And then we also have green and blue, yellow, and so on.
Okay, I think I want to use, I was thinking maybe I would use different colors for like, Comptime and runtime functions. So let's maybe use blue for normal. I like that red is a cozy color, or just use black and blue, or black and green, I think is fine. Black is like the default color, something is compiled, or like being compiled. And then green is Comptime stuff. 32. That should be fine. Yeah, not bold and not underlined. Oh, that didn't do anything. Okay. So apparently that is... Ooh, noise. So how does that bold and underline work? Bold is 1. And 4 is underline. Oh, I think you could just combine multiple of these with semicolons. So I just only do this for only green text. Yes. Yes. Amazing. Okay. I like that. I like that a lot. Okay, let's do that. Yeah. Let's move that into the compiler. Act to yogurt. Print status. This is a lot of stuff. Maybe I should do like... Yeah, this is more like the core functionality, defining functions and so on, and usually, for example, the write functions are defined underneath the more important functions. And this is definitely not the most critical part of, or like the critical aspect of a yogurt compiler. Okay, so write ANSI escape sequence is something we have. Move cursor to front, erase rest of current line, move cursor to next with an N, move cursor to previous with an N, and then max, I don't even know how to call that, like the lines that we printed but we moved up again, so then max preview, like pre-printed lines, maybe max, yeah, I don't know, pre-printed lines. Weird name, I know. Do that. And then for each print status of this compiler is basically what we were gonna do. Print stack of some compiler means we actually iterate over the compiler stack. Yeah, and then we switch on the entry, and that can either be compiling something, compiling the signature, in which case we just output the signature, or it can be running the signature, in which case we're actually going to do this. I'm going to print a green signature. Yeah. And then we move the cursor to the previous compiler stack len, and also save that as the next pre-printed lines len. Okay, yeah, nice. And then print status of this compiler would be called when, in several places actually, when you start compiling something. Yeah, you don't do this ad hoc printing, you just push that to the stack and then you say compiler print status, Also, when you're done compiling something, oh yeah, and also when you start running something, and when you're done running something. So now our compiler will actually print what it is currently compiling. Ooh, that is not what I expected. Oh, because there was like deep Comptime stuff. Okay, maybe we should limit that to, I don't even know, 5 or 10 entries. You know, print status, compiler stack limited to the first 5. So it will be stack to slice dot sub slice from 0 to 5, I guess. Yeah, move compiler to previous num printed. Oh, hey. Like, this is the declarative way to do that, but in this case I think an imperative one, imperative approach is actually more readable. So num lines we printed, you know, and if num lines unprinted is larger than or equals 5, then we just give an early break out of the loop. Otherwise, we print that, and we do num printed is num printed plus 1. And then we have these num printed. Yeah. That is kind of weird. I don't know why. Let's also add this artificial slowdown in here. Beautiful. Times 10, maybe. Oh, no new line after main int. Oh, I think the number of lines doesn't quite match the amount that we move up for some reason. Oh, because here we don't print a new line. That makes sense. You know, let's first clear the console and then. Okay. We're compiling main. And that calls Fibonacci of 3, that calls less than of 3 and 2, that calls compare, that calls built-in compare, yes. Then that returns, and then that returns. This is pretty cool. And then that returns, that calls then Fibonacci of, oh yeah, first subtracts 3 from 1, which calls built-in subins. This is so cool. Honestly. And then that calls Fibonacci of 2. And that calls less than. That calls compare. And it's super cool that you can see the difference between, like, you know, actually compiled functions are black,
and then the Comptime evaluated ones, which are green. Oh man. That's crazy. Still waiting for the Comptime stuff, for the runtime functions that get compiled. Maybe I should make this a bit faster, you know. List 1, 2, 3, and then oh no, that was a multi-line thing. Oh. I don't know how to deal with that. I mean, and string, let's just extract these. Yeah, I want to limit the signatures in the end and just print dot 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 if they are very long. I think that's a sane approach for now. But I don't want to do that here and down here, so I'm just gonna extract, you know, in this case I'm gonna extract false and the actual signature, and in this case I'm just gonna return true and the signature. And then I have this tuple where I can basically check if like you know, Comptime. I think that's better. Yeah, it's Comptime and signature. Dot A, and signature is that thing dot B, and then I can basically do this. Like if it's Comptime, then we want to print that in green, and also, you know, stop printing the green thing. But we want to print a new line either way, and we also want to treat the signature the same either way. Yeah. So how do we want to treat them? Well, we basically want to limit the signature. Like, you know, if signature.star.length larger than, what's the limit? Let's say 60. I think that's fine for now. Larger than 60 characters. 60 are fine. Then we actually want to print the signature.store.substring from 0 to 57 followed by 3 dots, so that the total is exactly 60. Otherwise,
yeah, we're just gonna do this. You don't handle running. I don't, okay. Oh, I don't. Indeed. No, I do. Yes. So now even for very long functions, just wait for the Fibonacci and the list. Yeah, for long functions, yeah, we will just print dots. I think that's fair. Not perfect, but what are you gonna do? Make that 10 times faster again. And also, I don't want to print the egg. Yeah. Okay, yeah. So it compiles the code. I think that's pretty cool. Oh man. I like that the terminal printing is really cool. Like super cool. You know? Crazy. You can really see the Fibonacci, like the top part stays stable, you know? That is amazing. Yeah. I mean, if I remove this, then you probably don't see anything, so, meh. But still, it's cool that this is possible. Yeah. Okay. Yeah, I think I'm gonna commit that. Yeah, not this, only this. Yeah. I'm gonna name it like terminal fun. Yeah. So cool. Okay, yeah, with that, I think I'm happy. Like, this was a lot of, you know, just refactoring the Comptime stuff. And I think like now it's looking pretty maintainable, pretty readable. Of course, there are still places where there are to-dos with, like especially these, you know, if this is Comptime, then do something, but that can never be reached because we now separated the runtime and compile time stuff. There were some of these code places where you can really simplify things. But I just want to get it, you know, work in the language and see how it feels with the current Comptime implementation and see if that works out. Okay. I guess. Until next time.